Okay, so and also I will comment briefly. So the discussion there were in the literature concerning the measurement of the speed of gravitational waves and the constraints that these observations led to scalar tensor theories. And then I will conclude. So let me start with the first part, higher order scalar tensor theories in a nutshell. So a brief history of scalar tensor theories. Before starting, I will just give you a very brief introduction and a very brief motivation, even though most of you knows probably this topic very well. But I like to remind to maybe the youngest of among us that general relativity is a beautiful theory. Mathematically, it is extremely well, it is extremely beautiful. It is described in terms of geometry. So there is a Lorentz geometry behind. And so far, it is in total agreement with today's observations. But we know that it has limits, as any classical theory. General relativity comes with its domain of validity, and we know that general relativity cannot describe the physics at the Planck scale, so at very short scales or very high energy, and we know that it needs UV completion. We need a UV completion of general relativity to describe these new scales. And the fact that we need this completion shows up in the fact that we have these singularities at the center of black holes, for instance, or at the Big Bang. And the presence of these singularities is really an illustration of the fact that general relativity is breaking down at very high energy. But also, we know that we have this problem at very large now scales, so very short energies, because we discovered the acceleration of the expansion of the universe, and we are in trouble when we try to explain these observations with general relativity itself, and when we use a cosmological constant. So we have this problem of the cosmological constant. I will not go back to this. And for these reasons, not only the question of the UV completion, but also the observation of the acceleration of the expansion of the universe, the last years, we tried to go beyond general relativity. And there is this huge activity concerning the construction of modified theory of general relativity to test the gravitational interaction at the different scales. And we had a lot of activities trying to find UV completions of general relativity, but also a different activity trying to show whether it is possible to deform and to modify general relativity to propose alternative to the cosmological constant to expand, for instance, the acceleration of the expansion of the universe. And in general, we like to construct theory and to propose deviation that we can constrain. So this is also the main, one of the main motivation of constructing alternative theories of general relativity. Also, I said that at the beginning that the general relativity is in total agreement with today's observations, which is completely true. But I like very much this cartoon due to Claudia Doran, which is extremely nice to explain that, in fact, even though general relativity is extremely well in agreement with observations, in fact, the domain where it has been tested is quite narrow. And in this graph, you have in the x-axis the mass of a system, in the y-axis the size of the system, and here at a point correspond to, of course, a mass and a size. And the yellow area here corresponds to the domains where general relativity has actually been tested. This is a cartoon. It is limited, but it is interesting to see that in fact, general relativity has been tested in a very narrow space of in a narrow domain of the parameter space. And for instance, in the large scales, at the scale of the universe, and also at small scales, we don't know whether general relativity is a good theory or not, because it has not really been tested at this scales. So there is a lot of reasons to believe that we can go beyond general relativity. So now, let me just tell you one more slide concerning the introduction of the motivation why we want to modify general relativity. And also one point which is really important is that we know that general relativity is unique. More precisely, general relativity with a cosmological constant, we know that it is a unique theory. And going beyond is quite difficult in some sense. Let me just remind you why. Because if we assume, so this is the first hypothesis, that space-time is of dimension 4, and if it comes with the symmetries which are essentially diffeomorphisms, so the physics should be invariant under change of coordinates. If we make the second assumptions that gravity is described in terms of a metric only, so a spin-2 field only, and if we make the assumption that the equations, the Euler-Lagrange equations, or in the case of general relativity, the equations of motions are second order, then we know that from the Lovelock theorem that the only possibility is Einstein gravity plus a cosmological constant. So the only action that can be constructed with these three hypotheses is Einstein gravity plus a cosmological constant. So if we limit ourselves to this hypothesis, then there is no much room available for alternative theories, and then we cannot construct something else. So the idea, as you can guess, is to relax one of these hypotheses to go beyond general relativity. And probably the simplest way to proceed is to consider scalar tensor theories where, in fact, the gravitons, so the metric, comes with a scalar field. So what we are doing here, we are relaxing the hypothesis that the gravitational interaction is described in terms of a metric only. We are saying now that gravity is described in terms of a metric plus an extra field, and we take it to be a scalar field. And in the context of dark energy, for instance, the scalar field will be responsible for the acceleration of the expansion of the universe, and so this will be responsible of dark energy. And in this talk, I will only consider these scalar tensor theories, and I will show how indeed they can be applied to the construction, to account for dark energy. But one more thing, in fact, not only we assume that the metric comes with an extra field, which is a scalar field here, but also we will also relax the hypothesis that the equations of motion are second order. We will say, okay, it is not necessary that we have second order partial differential equation to describe the dynamics of scalar tensor theory. You will see why this is an important assumption. And in fact, this second assumption is really in the center of the construction of those theories. So once again, why we are considering this kind of modifications of general relativity? So the motivations are manifold, but as I already said, adding a scalar is certainly the simplest possibility to consider modified theory of gravity, but also there are many other interesting scenario that would consider. Michael talked about massive gravity. Of course, we can consider massive gravity, but we can consider theories where you have two metrics, a vector in addition to a metric. You can also have extra dimensions. There are a lot of possibilities, and there are a lot of models that can be constructed beyond general relativity in these cases here. But what is interesting is that most of these models contain, in fact, a scalar mode somehow. And in a sense, scalar tensor theories can be recovered as a kind of decoupling limit of many other more complicated possibilities. Now, the reason why we are also considering this, we are also relaxing the fact that equation of motion are second order. The reason why we are considering this can be explained roughly from the following. In fact, we allow higher order equations because if we look at general relativity, the action is described in terms of the Ricci scalar, and the Ricci scalar is in fact constructed from second derivative of the metric. Of course, Ricci scalar can be given by the first derivative of the Christoffel, and Christoffel are first derivative of the metric. So then somehow you have second derivative of the metric in Einstein theory of gravity. Then it is natural to generalize scalar tensor theory in the sense that we can also allow for second derivative of the scalar field in the action. And if you do that, if you add second derivative of the scalar field in the action, you will naturally obtain higher order equations of motions. This does not happen to general relativity for some reasons that you know very well. But in the case of scalar tensor theories, if you add second derivatives of the scalar field in the action, in the Lagrangian, then you will get higher order equations naturally. And this will imply an extremely rich phenomenology that I will try to summarize quickly in the following. So before going to the details, I'd like to add that the landscape of scalar tensor theories has evolved a lot in the last 20 years since the discovery of the acceleration of the expansion of the universe, from Bronsdicki in the 60s to DHOST theories, and DHOST theories are now believed to be the most general physically viable scalar tensor theories that we can construct. So let me say a bit more about this. So indeed, the first theory, okay, now the idea is just to give you a brief overview of scalar tensor theories. What are these scalar tensor theories, the simplest one, and how we managed to obtain these DHOST theories. So first of all, the first theories that are very well known are first order scalar tensor theories. The simplest one are the Bronsdicki, so the traditional, the usual one. Simplest doesn't mean that they are trivial, they are extremely interesting. And also, these theories were generalized in terms of K-essence, and I will tell you what does that mean. So indeed, very quickly, in the 60s, Brans and Dickey, they introduced scalar tensor theories, which consist, yeah, maybe a question? No. So they consist in theories where the action depends on the metric and on the scalar field. And the Lagrangian takes this form here. So here you recognize the Ricci scalar. You have a function of the scalar field. You have X, which is the kinetic energy of the field, and an eventual potential of the field like this. So these were considered a long time ago in the 60s, as I said. And just at the beginning of the 2000s, they were generalized in terms of K-essence theory, and even a bit, yeah, you see here, I put the references on this work I'm mentioning here. So in the 2000s, people introduced the K-essence theories, which are a generalization of this action here. You see in this action, the dynamics of the scalar field is linear in terms of, the Lagrangian is linear in X, and X is the kinetic energy somehow. And naturally, people considered an arbitrary function G here in terms of phi and X, which can be non-linear in terms of X. And considering this kind of theories is extremely interesting because the phenomenology of this theory is very rich, and you can do a lot of nice physics with them. One thing which is really interesting is that when you consider scalar tensor theories, you have the possibility to have a non-minimal coupling to external matter field. For instance, if you consider a matter field psi, then the matter field psi can have a dynamics like this one if you consider a massless scalar field, for instance. And here, if A will be 1, you will get the usual minimal coupling, but you can have a non-minimal coupling, so a function of phi here, which modify slightly the coupling to gravity of the external field. And then if you have different coupling A to, if the coupling with if the function A is different from one species to another species of external field, then you will have violation of the equivalence principle. And this is extremely interesting. And of course, today we have a lot of constraints on this kind of minimal coupling. But nonetheless, considering this kind of coupling is extremely interesting if we want to apply it for inflation or for dark energy, for instance. So this K-sense theories and also the possibility to have a non-minimal coupling has been studied really a lot the last 20 years. But quickly after the, yeah, maybe there is a question by Ashu. No?
Yeah, hello. So can you hear me?
Yeah, yes, I can hear you.
Hello.
Yeah, go ahead, please.
Yeah. Oh, sorry, I don't know whether this is the right time to ask this question. There are these Galilean fields, right? So are those models of Galilean are the class of this those theories, or yeah, this is the yeah. So are those Galilean models are the class of this those theories, or I mean how those models are
So I'm sorry because
in a sense.
I cannot hear very well.
I,
Do
I
so?
guess
Yeah.
I guess the question is if Galilean models belong to this to your models.
Yeah. Okay. So
Right.
Galilean models, they belong to these models, but in Galilean the metric is not dynamical. If you want, a Galilean theory can be obtained. You consider those theories, but you fix the metric to be either the flat metric or any curve metric, and you obtain either the Galilean model with the flat metric or what we call generalized Galilean with a non-flat metric. So if you want, again, Galilean is a theory where basically you fix the metric to be Minkowski. Okay?
Okay.
So
Okay. Yeah.
let me,
Thanks.
yeah, no problem. Yeah. So now let me just go a bit further in the description of the history of this scalar tensor theory. So we first started with what I call first order scalar tensor theories, because you see in the Lagrangian only appears the first derivative of the scalar field only. But then sorry, I have a problem with, yes. In 2000, again, so these people, Dvali, Gabadadze, and Porati, they introduced this very celebrated model called now the DGP, or the Dvali, Gabadadze, Porati model, which was a kind of breakthrough because they realized that it is possible to have Lagrangian for a scalar tensor theory where, and in the Lagrangian, you have second derivative of the scalar field. And this is quite interesting. And in fact, I don't want to recall the context of this discovery, but basically, they started with a brain cosmological model, a 5D model. And if you consider a kind of decoupling limit of this theory, you get the cubic Galilean, which is the action, which is a dynamic system where the metric is coupled to a scalar field in that way. So here you recover the usual K essence model, but you have this funny new term, the box phi, and box phi cannot be removed by integration by parts. So you always have a second derivative of the scalar field in the action. And this is a novelty. This is a novelty because, as I said, we have higher order Lagrangians, but we still have second order equation of motion. So if you want, everything happens as in general relativity. Again, in general relativity here, if you write the Ricci scalar in terms of the metric, you will get second derivative of the metric. But the whole point of the Lovelock theorem is that even though you have second derivative of the metric in the Ricci scalar, you still get second order equation of motions. So if you want, the box phi here is a kind of equivalent of the Lovelock theorem somehow. So here you have higher order Lagrangian, but still second order equation of motions. And this has, this is not only a mathematical curiosity, it has a very interesting phenomenology, in particular to describe late time cosmology. This model has been completed, how to say, that are not available anymore if we want to compare them to observations. But still, they have quite an interesting phenomenology. Because if you add this kind of term in the Lagrangian, you will get a new scale in the theory. For instance, if you consider the simplest Lagrangian, this one, so you see here, G2 is only X, and the box phi, here, the G3 function is just capital X. So this is a simple example of this kind. you have a new scale, which is this lambda here, which is an energy scale. And you can show that this kind of dynamics can allow you to reproduce self-accelerations. So this means that you can have the acceleration of the expansion of the universe without cosmological constant. And for this to be true, you need to fix this scale to this value here, and H naught is the Hubble constant today, if you want. So it is possible to reproduce the acceleration of the expansion of the universe with this model here. Not only that, but also something which is interesting and something which also existed previously, but with different mechanism. Here you have a Weinstein screening, which means that in these theories, you can have a modification of general relativity at a large scales, which allows you to have a self-acceleration of the universe, but you recover general relativity inside a radius, which is called the Weinstein radius, which has this form here. And inside the Weinstein radius, you recover exactly general relativity, what you should have, because we know that general relativity is extremely well tested at the solar system scale, for instance, which happens in this theory, in this kind of series. So we have many hand raised. So I don't know if you ask, you can ask the question, please.
Okay. My question is about related to, in the beginning you mentioned about UV completion. So how this Lagrangian is related to UV completion? How it is activated fundamentally?
This is a good question. In fact, these Lagrangians here are not related to UV completions. If you want to, I mean, I talked about UV completion because this was a motivation to modify gravity. So if you want to modify gravity to account for quantum gravity, you have some strategies, and these strategies can be different from what we use to construct theories that would account for the acceleration of the expansion of the universe. So the theories that I'm considering here, they are not UV complete, they are not considered as UV completion of general relativity. UV completion, for instance, we have this very well famous, I don't remember now, these anisotropic models. Orava Lipschitz gravity. These are candidates for UV completions, but not these theories, in fact.
Okay, thank you. Can I ask another short question?
Yeah,
I mean, this Lagrangian, can it be related to some kind of f of r if you do some kind of this formal transformation?
Very good. In fact, f of r theories are related to Browns decay, to these theories. So you can have a relation between f of r and this kind of theories. But in general, higher order, I mean, these kind of theories are not related by this formal transformation to f of r. Okay, so these f of r are different. Yeah, from you cannot obtain f of r from this formal transformation of those theories in general. I mean, no, I will say it differently. You cannot obtain all those theories from this formal transformation of f of r.
Okay, thank you.
Welcome. So I may continue. So this was a very interesting model. So this DGP model, even though now I think it is ruled out by observations, but the idea of considering higher order Lagrangians, this is a very interesting aspect. And in fact, very quick, I mean, after the discovery of DGP, 10 years after, maybe, it was realized that it is possible to generalize the DGP model. See, DGP was this one, only this Lagrangian. But then you can consider different, like a more general Lagrangians that would contain second derivative of the scalar field. But if the DGP model is linear in the second derivative, you can have terms which are quadratic in the second derivative, like the box phi square. You can also have terms which are cubic in the second derivatives. And this is, I mean, and people, they try to find the most general actions that contain second derivative of the scalar field. And this is possible. And this was discovered first by Horndeski, in fact, in the 70s. Sorry, I have a problem with my maybe I should do that. Yes, very good. By Horndeski in the 70s, but then it was rediscovered by these people here and many other people in France and in Japan, where they show that it is indeed possible to have the full higher order scalar tensor theories that produces second order equations of motions. And these are now known under the name of Horndeski theories. So why these Horndeski theories are so interesting? Because they provide models for self-accelerations. So you can have self-accelerating solution without the need of a cosmological constant. You also have screening mechanisms that comes with this with these theories. So this is the screening that I described very quickly previously. And also at that time, so 10 years ago in the 2010, there were the belief that these Horndeski theories will provide the most general, relevant scalar tensor theories that we can construct. And this is very interesting because if you have the most general, relevant scalar tensor theories, then you have a frame to construct a complete parametrization of consistent modifications of general relativity. In some sense, you could have a frame to have an effective field description of modified theory of gravity. And this is extremely interesting because if you can say, okay, this is all the possible deformations of general relativity of the kind of scalar tensor theories, then you can parameterize all the possible deviations, then you can test and constrain all these deviations in a very complete way. And for this reason, these theories have been studied quite a lot in the context of dark energy, so to account for the expansion of the acceleration of the universe, the acceleration of the expansion of the universe, sorry, but it has also been studied for primordial cosmology, so in the frame of inflation, but also in the context of black holes. I will not have time to discuss about their application to black holes, but this can be done as well. But in fact, this is not the end of the story, because soon after the rediscovery of Horndeski theories, it was realized, people, they found new, viable, physically interesting theories that do not belong to the Horndeski class. And maybe you heard about the GLPV theories. GLPV is for Glaise, Langlois, Piazza, Vernizzi. And also these very nice mimetic theories of gravity. And also Kusketton and many other theories. And all these models, they appeared after Horndeski, but there were arguments to say that these theories are safe in the sense that they can be nice and interesting scalar tensor theories for describing dark energy, for instance, but they do not belong to the Horndeski class. So there were a need of a classification to understand what was going on, in fact. And I come to the second part of my talk, which is the DHOST classification. So I will be quite quick because I see that time is running. So now this is just the general picture of what we have today. So we manage with David Langlois to classify all higher order theories. And let me just explain you what this means. In fact, we managed to find the most general viable scalar tensor theories. I will tell you in a few seconds what viable means concretely. In these theories, the Lagrangian contain up to second derivatives. The equation of motions of these theories are not necessarily second order, but contrary to what happens for Horndeski theories contain higher order terms, but the equation of motion are second order. In the general case, again, the equation of motions are not second order, but at most only one scalar propagates in addition to the two graviton. And this is what we mean by viable scalar tensor theories. Viable means that we have scalar tensor theories where we have two gravitons plus only one scalar which is propagating. Okay. So the picture now is the following. You see here the green area correspond to the traditional, to the usual scalar tensor theories of the Brans-Dicke form or K-sense theories. So these were discovered in the 60s. So again, in the 70s, Horndeski classified Horndeski's theories, so higher order scalar tensor theories, which contain one scalar degree of freedom in addition to the two gravitons. So these were rediscovered by these people later in the 2010. Then I mentioned quickly other theories like GLPV or beyond Horndeski that were discovered in the 2014, where they found viable theories, so only one scalar degrees of freedom propagating in addition to the graviton, to the two gravitons. But these theories, they do not belong to the Horndeski class. And in the 2010-2016, we found those theories which encompass all known higher order scalar tensor theories. And what we claim is that if you consider any theory outside DHOST theories, they have an extra degree of freedom, and this extra degree of freedom is necessarily a ghost, which is called the Ostrogatsky ghost. So any other theories which do not belong to DHOST is necessarily unstable. But careful, this doesn't mean that all those theories are stable. I'm just saying that if you are outside those theories, you will have an instability, which is pathological, of course. But inside those theories, you have to check whether the theories are safe in the sense that they may have other type of instabilities, like gradient instabilities or ghost instabilities. And we analyze all these kind of instabilities in the DHOST theories. And what I can say from now is that in these DHOST theories, indeed, there are some theories which are safe physically because they don't have any gradient instabilities, for instance. But you can show that other types, there are some DHOST which have this kind of new other instabilities. By other, I mean instabilities which are not Ostrogatsky-like instabilities. Okay. So let me just tell you how this happens. So what is the idea behind the classification of those theories? So for that, I will use a very simple toy model. So let me start by this action here. So what happens when we add higher order derivative in the Lagrangian? So here you see you have a d action for only one point particle. So we have phi of t only. You have here the harmonic oscillator, and you add a coefficient alpha, which is supposed to be constant, times this higher order term. If you look at the equations of motions, because of alpha, you see the equation of motion for, phi comes with fourth derivative in the equation. So of course, as you have four derivative of the scalar field, you need four initial conditions. So these things, 4 is 2 times 2. And of course, this means that you have two particles which propagate in this theory. So in general, when you have higher order terms, then you have 2 degrees of freedom propagating instead of only 1. So what's the problem with that? A priori, why not having 2 particles and 2 degrees of freedom propagating? But if you look closely at the theory, you will see that you have an instability because the energy is not bounded neither from above nor from below. To understand why having higher order terms imply these pathological properties, you can show that, in fact, instead of considering this Lagrangian here, you can consider this equivalent Lagrangian. This Lagrangian is completely equivalent classically to this one, in the sense that if you look at the equation of motion for psi, and then you replace the solution of psi in terms of phi back to the action, you recover exactly this Lagrangian. Okay, so this equation, this Lagrangian is fully equivalent to this one. But what is interesting with this Lagrangian is that you can reformulate it like this, and you see now this Lagrangian contains one kinetic term with a positive sign and one kinetic term with a negative sign. When alpha is real, what we want, then you have plus kinetic energy square minus kinetic energy square. So this extra degree of freedom here is in fact a ghost. So there is an instability, which is pathological, and this ghost is the famous Ostrogatsky ghost. So whenever you have higher derivatives of the scalar field, and when you have only one scalar in the theory, then you will have this instability, and this is the Ostrogatsky theorem. But there is, in fact, one way to circumvent this difficulty. To understand this, let me try to explain you again, to give you a more elaborated model where now you have two particles, the phi particle and the q particle. Here you see you have the action, sorry, the first three terms is exactly the same action as the previous one. You add a dynamics for q, which is the dynamic of the harmonic oscillator, the usual one, and you add a new coupling like this one, which is a funny coupling between the second derivative of phi and the first derivative of q, whatever the coupling is. I mean, this is just an example, just to illustrate. If you look now at the equation of motion, you see that the equation of motion for phi contains the fourth derivative of phi, the third derivative of q, and the equation of motion for q has the third derivative of phi. So if I ask you how many degrees of freedom are propagating in this theory, it's not easy to guess. It's not easy to guess because you see it's not clear how many initial conditions you will need to integrate these equations. But in general, you can show that this kind of series propagate 3 degrees of freedom, the usual phi, the usual q, and you have an extra degrees of freedom, which is the famous Ostrogarsky ghost. So in general, again, you recover the instability that we had previously. But in fact, if we look closely at this action, we can evade the Ostrogarsky instability. Here, in fact, there is no instability. And let me try to explain you why. In fact, if you consider the variable capital Q defined by this thing, by this combination here, instead of the variable small q, you can show that this action is completely equivalent to this one where there is no higher derivative at all. So in fact, here, this theory, even though the equation of motions are higher order, even though you have higher order terms in the action, in fact, the action is called degenerate. And if you make a clever change of variable, you can show that there is no ghost at all. And this is the key ingredient for the degeneracy. And in fact, what we did in the case of scalar tensor theories is that we reproduced this analysis, the previous one, but with, in the much more complicated case where you have a metric and a scalar with higher order derivative in the action. But it is possible to reproduce a very similar analysis and to show and to see what are the conditions for an action of this type. Here you see where you have a second higher derivative of the scalar field like this. What are the conditions on the functions A1, A2, N3, A4, N5, and 3, all these 3 functions for the theory to be degenerate, which will ensure that there is no Ostrogarsky ghost propagating in the theory. To be more precise, the degeneracy condition is a necessary condition to avoid the Ostrogarsky instability, but it's not a sufficient condition. But I don't want to enter into the details because I'm running out of time, and I'd like to give you more physical, some physical application of this. But before that, so those theories are these scalar tensor theories where you have the degeneracy, so only 3 degrees of freedom are propagating. And what we found is that, in fact, if you consider only quadratic actions, by quadratic, I mean that only the quadratic term in the second derivative of phi appear in the action. You have two types of those theories, type 1 and type 2. Type 2 are completely independent from Horndeski theories, and we show that this type 2 theory are in fact unstable because they have no Ostrogarsky ghost, but they have necessarily a gradient instability. So there is another type of instability that rule out completely these type 2 theories. And so we only remain with type 1 theories, and we can show that all those theories in the type 1, they are in fact related to Horndeski by general, disformal, and conformal transformation. So we have this picture. If you consider Horndeski theories and you make an arbitrary disformal and conformal transformation like this one, where C and D are arbitrary, you get the general DHOST in the type 1. And conversely, any DHOST theory in type 1 can be related to Horndeski by a clever choice of disformal transformation of the metric. And of course, the notion of degeneracy is fully preserved by this formal transformation. Okay. So this is just the main information that I like you to. I wanted to tell you about the construction of DHOST theories. Of course, I didn't want to give you the technical details of all that, but if you have questions, I'm happy to try to discuss them. Just because I'm having 2 more or maybe 1 more minute, I'd like to tell you about the cosmological applications and implications of this constraint. I will just not talk about astrophysics because I will not have time. So now we can try to study the cosmology of these theories. So the first thing that you want to do is to see whether you can recover the acceleration of the expansion of the universe, and you can have self-accelerating solution. So for the background, this is easy. You can show that indeed you can find those theories where you have an expansion of the acceleration of the expansion of the universe, which is in total adequation with what we observe today. What is more interesting is the study of the cosmological perturbations. So looking at perturbations which are linear about a cosmological background. So you can do the general analysis of the perturbation. You can show that you have 2 types of perturbation, the scalar perturbation, zeta, and the gravitational perturbation, the tensor perturbation. So here you have the graviton. And of course, at the linear level, the dynamics of the scalar perturbation is fully decoupled, is completely decoupled from the dynamics of the tensor perturbation. You have a spin 2, you have a spin 0, they do not see at the linear level. And the dynamics of the scalar is governed by this action. So here you have zeta square minus here you have the speed, the sound speed. So the scalar perturbation propagates at the speed cs, and the tensor mode here gamma. So the gravitons, they propagate at a speed which is ct. And in general, ct is different from 1. It's not so gravitons in those theories they do not propagate at the speed of light. And the physical reason is that now space-time is fully filled. You have scalar fields everywhere. So everything happens as if the gravitons are propagating in the medium. So the medium is formed by the scalar perturbations, if you want, so the fifth force. And so gravitational wave, they feel the fifth force, and then the speed of the propagation is different from the propagation in vacuum, which will be c = 1 as for light. So in general, ct is different from 1. And of course, we had this very famous event. So the 2 neutron stars merging to form a new compact object. And we were able to show that tensor modes, they propagate at speed of light up to a very, very tiny value, as you can see here. So the difference between ct and 1 is lower than 10 to the minus 15. So this imposes a very severe constraints on those theories. If we take this constraint seriously, if we say that, okay, ct is 1, then in fact, many of those theories are ruled out by this constraint. But we have, and I'm going to finish with that, so I'm sorry to be late. In fact, we have to take this constraint very carefully, because with LIGO and Virgo, we are probing those theories at the limit, at their limit of validity. And this is the famous rainbow argument, which was very well explained by Durham and Melvin a few years ago. And in fact, they show that indeed, if you consider a dose theory that accounts for dark energy, it has a scale, lambda, and below scale lambda, you cannot trust the theory anymore. And the scale, which is the scale of validity of those theories, is given by, it is at the order 100 Hertz, and 100 Hertz is also the typical frequency that are analyzed by LIGO and Virgo. So we are really at the domain of validity of those theories. So it's not clear that whether the constraint I've just talked about is something that you can apply to those theories. And it is very possible that, in fact, those theories there are modifications at very large scale. So at large scale, you can have a theory where the speed of propagation is not 1, but at short scale, at larger scale, high energy scale, you recover the Lorentz invariance. And when the theory is Lorentz invariance, then you recover the fact that the waves are propagating at c=1. So this is the rainbow argument. And again, when we look at the LIGO and Virgo measurement to constrain those theories, we have to be careful because we are probing the theory at the limit of the validity. Okay, and I think as I'm running out of time, I will not talk about astrophysical tests. And let me just finish by showing you this last slide. So thank you for your attention. And again, I'm sorry for the delay.
Okay, thank you, Karim. But I suppose we have a couple of minutes for a couple of questions. So if somebody wants to ask something, then please do. Shravan, okay.
Yeah. Hi, thanks for the nice talk. So I have a question about how to distinguish your models with IR non-local models.
IR non-local models?
Yeah, these models with 1-over box operators. I mean, for example, Maggiore model.
Yeah, okay. No, these are completely local in the sense that you see, maybe the notation is a bit confusing, but when I write box phi square, this means that box phi times box phi is not box square of phi. So this is completely
yeah, this I understand. I'm asking about observationally how to distinguish the two models. So
at the observational level, I don't know, because I mean, of course you can test these theories at the level of the background, but this is too, I mean, the constraints are very, very few and not very interesting. And then you can constrain this model at the level of the perturbations, and the effect of these theories on the perturbation has been analyzed very well. And I don't know what would be, because I don't know well enough the non-local theories. I don't know what are the analysis, how perturbations, what is the dynamics of the perturbations in the non-local theories, just to see whether we have differences with the dynamics of the perturbations with these theories. But it might be that the dynamic of the perturbation are very similar for DHOST and for non-local theories. This I don't know. And if this is the case, this would mean that we might have to go maybe below the, I mean, beyond the linear level to see a difference between the two theories. But I don't know. Yeah, sorry for that.
Oh, it's okay. Can I ask another short question? I mean,
quickly.
It's fine.
Quick question.
Okay. Yeah. How the screening mechanism works in this theories? I mean, for the local to recover the local solar system constraint.
Yeah, but this is maybe a very, I mean, not easy to answer in few minutes. So the screening mechanism here, in fact, what you can show basically is that these theories are non-linear, because you see you have a coupling between X contains 2 times phi and box phi contains, of course, 1 times phi. So here you have highly non-linear theories if you look at the structure in terms of phi. And the non-linearities of the theory are responsible for this Weinstein screening, in fact. If you want, I can give you some references where this is very well explained. In fact, this is a reference where this is a review on those theories, and you have a chapter on Weinstein screening, and where you can see technically where does the Weinstein, where the Weinstein screening comes from, I think. But the idea is that they really come from the non-linearity of the theory.
Okay, Ludovic, you have a question? Please do.
Yes. Can you hear me? Yeah.
Yes.
Okay, fine. So first of all, thank you very much for your very clear and really interesting talk. My question was, So about those theories, of course, on basically on your slide 15, you explained that there are, I guess it's 15. Yes, it's this one. That there were two types of those theories, and that the one type that was interesting could be related to Horndeski gravity up to these disformal transformations. And so, does this means that all the say interesting or non-pathological, I don't know, those theories are actually equivalent to Horndeski, or it's probably more subtle than that? Or
yeah, this is a very good question. In vacuum, yes, in the sense that if you look at those theories and you not couple them to external field, I totally agree that all interesting those theories are fully equivalent to Horndeski. But if you couple now the DOS theory to a matter field, then theories will be different, because you can have a DOS theory minimally coupled to an external field, but then if you make this disformal transformation, the DOS theory will be transformed into Horndeski theory, but the matter will not be minimally coupled to the metric anymore. So okay, if you want to say it differently, all those theories coupled to matter field are equivalent to Horndeski plus a non-minimal coupling to matter.
Yeah, okay.
So in that sense, they are equivalent to Horndeski. Yeah.
Yeah, but up to some maybe weird coupling to matter. Okay.
Exactly.
Okay, thank you very much.
Okay, Karim, thank you. I guess we should continue. So thank you, Karim. Thank you. So the next speaker is actually myself, but I will try to do it more quickly then. So Karim, can you stop sharing? So you stopped. Okay. Okay. Fine. So this is my screen, and so okay, full screen. So I will present you results of published with in a couple of papers with Alexei Starobinsky, Sergei Sushkov last year, and with two other younger guys and the same group this year. And this is precisely about Horndeski models. So there is this. So let's take usual general relativity, and let's continue homogeneous and anisotropic cosmology of Bianchi 1 type. It's the simplest one. So there is the metric with three scale factors A1, A2, and A3. If they're all equal, then the universe is isotropic, otherwise anisotropic. And then one defines the scale factor and anisotropy parameters in this way. And then if there is an isotropic energy momentum tensor, then the Einstein equations boil down to the Friedmann equation of this type. So there is Hubble on the left. On the right, there are anisotropy contributions, and then the energy density. And the equations for the anisotropies. And these have the total derivative structure, and they can be integrated. And this gives beta dot as a function of scale factor with the integration constant C plus and C minus. And when we take this and inject into the Friedmann equation, then we obtain this thing. We obtain that the Hubble on the left is proportional to the contribution of anisotropies, and there is the energy density. And it's clear that so one can see that the anisotropy contribution decreases very, very fast when A increases, and therefore at late times anisotropies become completely irrelevant. However, by the same logic, when we go backward in time, anisotropies become dominant near initial singularity, and that is why people usually think that that initial state of the universe, the state which is preceding to inflation, must be strongly anisotropic. This argument seems to be quite robust. However, we discovered a problem with this. Not a problem, but the different conclusions can be obtained in Horndeski theory. As a starting point, we choose the simple Horndeski model of G5 type, which contains the Einstein tensor in the Lagrangian. And precisely in this theory, the speed of gravity waves is not equal to 1, but I will explain what happens. Now, assuming that everything is isotropic, so if the three scale factors are the same, the Hubble law assumes this value, and the scalar field equation actually also has a total derivative structure. It can be integrated once, and the integration gives a constant which can be called scalar charge. Now, if this constant is 0, then the left-hand side should vanish, which is possible either if phi dot is 0, and in this case, the Hubble is determined by the cosmological term, or the left-hand side vanishes if this bracket vanishes, and then phi dot is this, and Hubble is also constant, but this constant is not determined by the cosmological constant, not by the lambda term, but by the coefficient in front of kinetic term. So for this second solution, lambda term is effectively completely screened. It becomes irrelevant. And so the scalar field acts as an inflaton. The essential difference is that there is no inflaton potential, and then the role of the potential is driven by, is played by this coefficient, and so in front of kinetic term. That's why the model is sometimes called kinetic inflation. So one can speculate that this alpha is given by some quantum corrections, and then therefore it's small, therefore the h squared is large. So this is in the case if the scalar charge is 0. If it's not 0, then the solution of these two equations interpolates between the kinetic inflation in the past and the usual inflation in the future. And so the solution is something like this. The Hubble is large and constant in the past, and then it decreases and becomes constant and small in the future. So you have a primordial inflation here, and then the late time actual inflation in this region. Now, everything is nice, but the problem is that if you consider the small fluctuations around these backgrounds, then we discovered that in both in scalar and tensor sectors, the square of the speeds of sound become negative at small times. Therefore, the model contains gradient instability at early times. At late times, on the other hand, speeds of sound approach unit value, and in particular, the deviation of the gravitational wave speed from the speed of light is proportional to the following ratio. And if you take for the late inflation actual value measured by value, and for the early Hubble, well, the value predicted by the inflationary models, then we get the number which is many orders of magnitude less than the experimental bound mentioned by Karim in his talk. Therefore, these models are actually in perfect agreement with the observations. Now, fine, this is about isotropic. And now, the last remark is that this model, also mentioned by Karim, is that this model can be written in the equivalent way, and it can be mapped to the DHOST model in such a way that the speed of gravity waves in the image theory will be exactly equal to 1. But this is just a remark. Now, let's see what happens with the anisotropism. We again take Bianchi 1, and then the Friedmann equation becomes this. Scalar field equation becomes this, can be integrated once. And then the anisotropy equations can also be integrated once. And then this gives again the integration constants. And now, when we express the anisotropy parameters from from this equation, then we obtain the following result. And now the second factor becomes infinite where A approaches, if A approaches 0. But it's possible that this phi dot approaches infinity as well, in such a way that the product stays constant or even vanishes. And in this case, if this is the case, then the anisotropies will not be enhanced near the singularity, but on the contrary, they will be suppressed. And in fact, when we solve these equations, these equations are actually algebraic. They can be solved in parametric form, and then we discover the following solution. Here, S is the function which determines anisotropies, and we see that it vanishes both at late times and at early times. And in fact, at late times it vanishes as usual as 1 over a cube, but at early times it approaches 0 as a to the plus a cube. So it vanishes in both limits. Whereas the Hubble is before interpolates between the kinetic inflation in the past and usual inflation in the future. So it's interesting result. It contradicts the common belief. So universe turns out to be anisotropic only during the short period of time. And in fact, if we pass to the physical time, t, then the anisotropy period becomes shorter and shorter if we increase the anisotropy amplitude, because if the anisotropies becomes higher, then the Hubble becomes higher because the Hubble receives contribution from anisotropies, and therefore the anisotropy period shrinks. So this is finding, and now one can ask what happens in the beginning. Since the anisotropies are damped at the beginning, therefore one can think that the initial state of the universe is isotropic. On the other hand, we know that if it's isotropic, it should be unstable with respect to inhomogeneous perturbations. Therefore, it cannot be isotropic either. And so we are bound to conclude that the initial state of universe in such models should be inhomogeneous. And this requires a separate study. Now, this was a particular Horndeski model. Now let's consider general theory. General theory, as was explained by Karim, general Horndeski theory is defined by the following Lagrangian, and this Lagrangian contains second derivatives, squares of the second derivatives, and then cubes of third powers of the second derivatives of the scalar field. Now we can do again. We do the Bianchi one case, and when we do the variation, and then we discover that the Hubble law becomes quite complicated. But the good news is that the anisotropy equations still can be integrated, still have the total derivative structure. But this time, after integration, they receive non-linear in the anisotropy terms. And then the scalar field equation can also be integrated under the following conditions. Now, if we do, then the natural question is, what happens with the anisotropy damping? Are they damped or not? And then one has to consider several cases, and then the two major cases. The basic difference is whether this coefficient vanishes or not. So first, if it vanishes, then the anisotropy equations are linear in the anisotropies. And then we solve them and obtain equations, anisotropy in the following form, where G in the denominator is arbitrary function, which determines the value of G4 and G5 appearing in the Lagrangian. So in the simplest case, we choose this function to be just a constant. Oh, sorry. And then the anisotropies are proportional to 1 over a cube, and therefore they grow near singularity. And then we injecting this to this equation, we recover the form of G4 and G5, and we discovered that this covers all conventional theories. So this usual vacuum general relativity with the conventional scalar field, Chi-sense theory or KGB theory. In all these standard theories, the anisotropies grow near singularity, and in all these theories, the gravitational speed constant, gravitational speed wave constant speed is 1. So nothing interesting for us. To get interesting effect, we have to consider Horndeski models, including the squares and cubes of the second derivative of scalar field. And in the simplest case, we recover the model I presented in the beginning. But one can also go further, and then one can analyze more general models with non-trivial G5, depending on X. And in this case, the equations become non-linear in the anisotropies, and then they require separate analysis. It's actually quite complicated, but we considered another model with G5, and it's also shows the phenomenon of kinetic inflation with Hubble constant in the past and in the future. And this time we have a very good news. We discovered that in this time the scalar sector is completely stable, and this gives us hope that if you play more with these functions, probably we may obtain completely stable model of this type. But it is still an open question. Well, here are the anisotropies, and okay, this is it's fine. And just in the remaining few minutes, 3 minutes, this is the last thing we did was the inclusion of spatial curvature, Bianchi 9. So Bianchi 1 is good, but what happens if you consider a more general case? We take a Bianchi 9 metric, and then in this case, the anisotropies induce the potential in the equations. And if you again consider the same simple Horndeski model I started at the very beginning, then the equations boil down to the following three: the Hubble Friedmann equation, and then the equation for the anisotropies, which this time they do not have the second derivative, the total derivative structures, because there is a potential on the right. But the scalar field equation can still be integrated. And now, if the scalar field is 0, then and then if you set anisotropies to 0, then the simplest solution is de Sitter, which in these coordinates has the form of the bounds. So the universe first shrinks up to minimal size and then expands. Now, if you switch on anisotropies, then small ripples around the bounds appear. And if if the anisotropies becomes large enough, then the character of solution changes, and it starts showing, it becomes singular, and it shows infinite sequence of anisotropic oscillations. This is the famous Belinsky-Khalatnikov-Lifshitz phenomenon. Chaotic behavior near singularity. And so the singularity is approached by infinite sequence of oscillations, and during each oscillation cycle, the universe is approximately Bianchi 1. And during each cycle the derivative is negligible, and it becomes important only when the cycles change, and this changes the value of integration constants. And now the question: this is the vacuum theory. What happens if you switch on the scalar field? Surprisingly, we discover exactly the same phenomenon. This is the result of numerical integration. And then we see that even with the scalar field, there are these oscillations. And at the first sight, this contradicts the fact that in Bianchi 1, anisotropies should be suppressed. But in fact, the catch is this, because now we have a spatial curvature, and this spatial curvature appearing in the solution ensures that near singularity, phi dot grows not as 1 over a cube, but as 1 over a. And this is fast, but not fast enough in order to suppress anisotropies. Therefore, the anisotropies stay unsuppressed. So, and finally, here are our conclusions. So we conclude that anisotropies are not always damped in all models. They are screened in Horndeski models whose Lagrangian contains quadratic and cubic in second derivative terms. This doesn't mean that the universe initial space is isotropic. It's rather inhomogeneous. The gravity waves move with the position-dependent speed in these theories, but at the present value, this speed is very close to 1. And then this behavior is removed by the spatial curvature in the Bianchi 9 case. So that's all what I wanted to say, and I don't want to abuse my time. And therefore, I ask you to ask questions if there are some questions. So Ludovic, please. So is this you, or this remains from the?
Oh yeah, I think that remains from my previous question.
Okay,
Sorry,
okay.
I should lower my end.
Okay. So, if there are no questions,
can I ask
okay.
question?
Yes, please do.
So actually, in your Lagrangian, you have cosmological constant. So in the late time, you reach lambda CDM.
Right. Yes. Yes. It's just the same cosmological constant as usual. So at late times we have lambda CDM, and we are not going to resolve the cosmological constant problem. But the primary inflation is different. So the late inflation is the same, but the primary is completely different. So this is the point.
Okay. Thank you.
Okay, fine. And so with this, we are staying perfectly in time. Therefore, I invite now the next speaker, who is Alexei Koshelev, to, I suppose, he is online. Yes, please, Alexei.
Hello, do you hear me?
Yes, but you should share your screen.
Yes, sure.
Then I mute myself, and then please.
Do you see it?
Yes, I do.
Okay. Okay. So is it okay like that?
You can I can see everything.
Okay.
At least I suppose the others also. Yeah. Just start.
Okay. So should I start?
Yes, of course.
Yeah. Thank you very much, and thanks for inviting me. And it's my pleasure to present my current work here. And this will be mostly about analytic infinite derivative gravity. I will try to convince you that infinite derivatives may be the only way to avoid ghosts. as long as we keep principles like diffeomorphism invariance, for example, and stay in the framework of the Riemannian geometry.
Sorry, just a stupid question. Ghost where?
In gravity, you will see.
Okay.
So I will be talking about gravity, and I will be talking about generalizing gravity because I want to attack the question of quantizing gravity. And for this purpose, just GR is not enough, you see. And mainly this is based on recent papers in collaboration with Sravan, Kumar, Alexis Tarabinsky, and Anna Tokareва. And so I will be talking about the this is the Lagrangian, which I present you here. These two lines, the first line is GR and lambda, and this we pretty much know, but the rest is pretty much unfamiliar in a sense that it's not very often to consider f of boxes here, where box is the Lambertian operator. But nonetheless, this is an action which I want to put forward as an action
We can't hear anything. Alexei, maybe you have connection problems.
to choose something. Sorry?
I think you have connection problems. So please continue because there was a stop. Yeah. Okay. Continue.
Yeah. So it's not a problem in general to have this action, and it's not surprising also to have quadratic and curvature action, because when we have quadratic and curvature action, this somehow resembles model by Kelly-Stelle, and proven that quadratic and curvature gravity R squared is in fact renormalizable. So it's quite natural to expect that something can be improved there, because in his approach it was a ghost. And let me now say why we can arrive to the section from a totally generic perspective. And the idea is, as long as we can consider a generic action for gravity, which contains generic constructions on curvature and generic operators constructed on covariant derivatives in somewhat indeterminate products and sums, then upon some algebra, which was just a routine procedure, it was possible to show that action from the previous slide appears as a limit in which linear perturbations around Minkowski or de Sitter can be considered. And if we keep Minkowski or de Sitter like our background, then we can even find second order variation. This is the second order variation for spin 2. And this is the operator which somehow sandwiches H mu transverse and traceless. And this operator, apart from box minus R over 6, canonical to GR with lambda, has also P of box. And P of box is this lengthy expression, which I colored a little bit. This unit is just what you would get from GR. And this green, what you would get from R squared gravity, local R squared gravity. And the rest is what you would get from whatever generalization with whatever FW of box. And in the case of Kelly-Stelle in 1977, the story was that W squared, so Weil tensor squared, was included in the action. And then FW equal 1 corresponds to just such P of box. It's nothing but yet another linear polynomial in box, which means that essentially second pole arises. And this is why there was a ghost in the tensor sector. Analogously, we can consider somewhat related to spin 0. And this is practically whatever about scalar degree of freedom like in F of R gravity. And again, we have the same structure, that something, this unit comes from R squared, just from GR, green term comes from local R squared gravity, and the rest comes from whatever possible more generic function fr of box. So let me now return a little bit to my action, how it looked here. So you see, whatever we would know about perturbations comes solely from these two pieces, RF of box R for scalar and Weil tensor FW Weil tensor for graviton. This piece, in fact, can be in principle eliminated around Minkowski or de Sitter, so around maximally symmetric spacetimes, and almost eliminated in dimension greater than 4. A dimension greater than 4, it should be kept in the form of L mu squared, and L mu is just traceless rich tensor. So with all of that set up like that, we see that in principle here we have understood what would be the most generic propagator in whatever initially arbitrary gravity theory for graviton around Minkowski space. The question is there any way that we can somehow avoid ghosts in this construction? In the meantime, let me mention that infinite derivative quadratic in curvature action, we can in principle find some other solutions. So even though we advocate this action as a limiting case in Minkowski space, in principle, we are not forbidden to consider this action on a more general footing, and then we will find that there are some other solutions, and in particular, solutions which satisfy box R equal R1R substitution are solutions here. And as such, we immediately show that Starobinsky inflation, which exactly solutions satisfying this condition, is a solution also in our more generic framework. There are some other interesting solutions here, like, for example, ghost-free bounds, or some interesting study related to absence of singularity in centrally symmetric solutions. But for the time being, I propose the idea. The idea is the following. Let's say, quite seriously advocated for maximally symmetric spacetimes, I want to ask a question: what will happen if we will consider this action generically, and we'll consider it as a starting point to quantize gravity? So in some sense, I want to say that this action of the first, perhaps everything I need to quantize gravity. And with this quite brave proposal in mind, let me compute propagator, and let me do a little bit of trick compared to previously shown expression for vectors, or sorry, for tensors and scalars. And let me try to compute kind of the same propagator, but let me try to do a 1+3 decomposition, which I can do in principle, even though I have in mind Minkowski for the moment, but perhaps I can do the same in Friedman universe as well. And then I will see that if I do this in 1+3 decomposition, which is essential for studying cosmology, then I will see that tensors, but now tensors with respect to three-dimensional symmetry group, and scalars acquire such non-trivial operators here for OS and OT. Seems like not so easy to study, but the question is here, finally, can we somehow understand what can be these form factors? Because the only thing which we could imagine before, since we were saying we are considering analytic dependence on derivatives, that these analytic functions at zero. The question is, can we somehow, do we know about something about them? And here's the explanation how we think about these operators. Imagine for the moment that we consider just scalar field theory with box minus m squared kinetic operator. This is quite nice theory, and in the minus plus 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 signature, it's a good scalar field. Then we pretty much know that would it be not a box but minus box, it would be a ghost. Would it be not minus but plus m squared for real m, it would be a tachyon. But also we know that would it be two factors like box minus m squared and box minus mu squared, this is definitely one normal and one ghost field. And this is related to known for a long time Ostrogradsky instability. Obviously, if we put here something higher polynomial in box, it will not solve the problem. It will just produce more normal and more ghosty fields. The idea is that in principle, things will look differently if instead of box minus m squared, we will consider box minus m squared multiplied by somewhat exponent of entire function of box, where box is always our D'Alembertian operator. If it is exponent of entire function, then it is a function which doesn't have zeros on the whole complex plane. And being as such and being inverted, it will not produce new poles on the whole complex plane. Which means if we return back to our previously derived expressions for scalar and tensor propagators in ADM decomposition, and I somehow like better ADM decomposition because it immediately shows me physical graviton with two polarizations, then the only thing which I must require is to equate whatever obtained for scalars to this expression, which means some massive excitation with mass mu squared and exponent of entire function, and then equate tensor propagator just to this, because I know that no extra mode is allowed, because one, thanks to box, already exists. If I now try to express Fw through exponent of sigma, and also try to eliminate any possible poles here, so that I don't ask a question whether operator is invertible or not, then I come to these simple conditions. What is Fw and what is f of box? Moreover, they become connected. And technically speaking, my whole story is now defined up to sigma of box, some entire function, one entire function. What is essential here, in this construction, I have no way to avoid extra poles if Fw is not infinite derivative function, which essentially means if I now come back to my original Lagrangian, I claim that as long as I stay in the framework of Riemannian geometry and diffeomorphism invariant action, I will not be able to avoid ghosts as long as I do not include infinite number of derivatives, at least here, inside of product of two Weyl tensors. But actually, I should not maybe bother about this as long as I can understand how do I work with any system which contains infinite number of derivatives. In principle, it's not a big deal to have infinite number of derivatives. This in some sense equivalent to integral equations if I look at these equations of motion, or they can be solved by some other tricks, and we have found several solutions, even in exact analytic solutions. So it doesn't look like hopeless, but there is a question: what happens in a quantum system? Let me consider a quantum field theory with infinite many derivatives. And this was done quite recently in collaboration with Anna Tokareva. What was done here, it was considered action like this. The only difference with previous slides I changed signature just because this particular paper was written in other signature, because my collaborator is definitely person from quantum field theory community, and there the signature is more common stuff. And with some simple restrictions on functions which do not actually squeeze any generality of consideration, what we want to see, what happens to this theory, because the problem is that since this function has infinite powers of box, it almost automatically means that we gain essential singularity at infinity. So the point is that yes, we have avoided poles in the propagator, but we did not avoid essential singularity at infinity. And the question is how we deal with this. And this is a trivial thing of a Ted-Pole graph, in which we try to see whether weak rotation, canonical weak rotation works. And apparently it doesn't. And in fact, it indeed does not, because in order for it to work, we need to somehow make integral over large R to be equal 0. It's not very easy to achieve, even though not impossible. We should impose some condition which would relate to us, which would make for us this integral 0. It's not impossible, but given that any new Feynman graph will generate a new condition, we will end up with infinitely many conditions. It's not what we want. And we go to employ other procedure suggested in a paper by Pius and Sen in 2016. And the procedure assumes that all the computations related to loop momentum must be done in a Euclidean space, and then results should be analytically continued to Minkowski space as long as we want to find somewhat physical result with respect to external legs of the Feynman graphs. Having this procedure applied to this particular Lagrangian, what we find out that as long as we compute amplitude, the answer appears, and this particular answer corresponds to a form factor, this f of box, just exponent of box. And this is a full answer which we need. This answer shows nice properties in the following sense. First of all, this piece is real. So when we will speak about amplitude, it will become imaginary. And it means it will absolutely satisfy the statement of the optical theorem as a first check. As a second check, when alpha, this parameter goes to 0, and essentially f of box is becoming just a unit, we nicely restore logarithm of z and z as a Taylor expansion of integral exponent here. So this will restore logarithm of p squared, and this and other terms will, and also here we will obtain logarithm of p squared, and as such we will restore explicitly logarithmic divergence as it should be in the cutoff method, because in some sense this form factor plays the role of the cutoff after a box becomes after a box greater than 1 over alpha. As such, it looks like that we have obtained a result which satisfies at least some, let's say, boundary checks. To make our progress even more, we decided to see what we can do for a generic form factor. And to our surprise, it was possible in this particular theory to compute the fish graph for a generic even form factor. And we have reason to assume why this function should be even with respect to its argument. And even this nasty integral, which is written here, can be performed over x, even though it's not too much illuminating, but it will be written as a summation of few fractions. But what is a little bit more surprising, what is not obvious from the very beginning, whatever we obtain here, which may be very cumbersome, the leading contribution, the leading contribution which indicates what the decay of our amplitude will come from this particular graph, from this particular integral from the last one, and it will show that there is a universal 1 over p squared term, and this holds for any even function f of box. And then we also could check that whatever we present here as long integrals can work. And in particular, we have checked this numerically for function exponent minus p to the fourth, where, I mean, p squared is a Fourier image of the Lambertian, and p to the fourth means just box squared. And also for this quite an interesting function, but this function is a peculiar one. This function has a property that even though it's exponent of somewhat not so obvious agglomeration of functions, it is indeed the entire function, first of all, but second, the whole object falls polynomial at infinity, which opens a door to at least rely on something like power counting in this model and, for example, avoid strong coupling regime. On contrary to stuff which happens in just exponent of box. Having this obtained, we also can say that similar trick of inclusion of infinite derivatives can sometimes help in models which are not exactly related to just non-local gravity. And this was an attempt, again, in collaboration with Anna Tokareva, to improve model of Higgs inflation, improve in a sense to render it renormalizable thanks to inclusion of this factor here, because otherwise arbitrariness of potential makes model generically non-renormalizable. The hope here is that suppression with higher powers of momentum will make them renormalizable. And here, what we found from this consideration, we found that in principle, even though we are quite successful in other studies, it may be essential to understand that as long as we can easily define, for example, vacuum and easily obtain what does it mean ghost-free condition in a vacuum, it seems like there is an issue here, which is not very well understood for the moment, that if we depart from the vacuum and look for the whole background and, for example, attack problem like effective potential or problem of, for example, one loop effective action or stuff like this, then we will inevitably hit a problem that as long as we have departed from a vacuum, we will not have absolutely ghost-free picture, because the condition that there are no ghosts at all means that this particular equation, being solved with respect to box, has just one solution. And if you look to this particular equation, which is written here, this is generically possible if right-hand side is 0. And you can do it in some certain points, in some discrete several points, but not everywhere. So the question is what to do during all the rest of the evolution of our model. What does it mean? What does it mean at all that we have 1 degree of freedom in a vacuum and seem like observe somewhat extra once we depart the vacuum? And the answer to this particular question is simply, I don't know. But what I know and what we have found is that as long as at least in this particular example, we can organize that in each and every point here for every value of phi, which essentially transforms here to m squared, we can make such a relation between possible roots of our equation. Then when I say our equation, I mean this equation as algebraic equation with respect to box. Then it looks like as long as we organize this condition to happen, which exactly says that imaginary part of some mass of some excitation squared should be less than 9h squared real part of the same mass squared, then we can guarantee that whatever these new, let's name them, would be excitations, whatever they are, ghosts or not ghosts, and actually following the Lagrangian, it's not even trivial to see what they are, but what we definitely know with this condition, they will not have growing classical solutions. And as such, they will not be harmful because they will not be able to destroy the main contribution to the evolution. So again, you see, the point is, it's not like in many models, people often claim that whatever extra modes, if they're heavy, then they're not excited and that's it. No, it's not like that. Here, it's a bit more difficult. It's not enough to make them heavy. You also have to organize that imaginary part squared of their mass is less than a real part of their mass. Then things go well. And if this happens, we can say with great confidence that whatever we have here is a stable evolution. So let me conclude here, since I'm coming to end of half an hour. It was an attempt to discuss generalizations of gravity and attempt to prove that if we need infinite number of derivatives to avoid ghosts, and attempt to show nice properties of this model related to absence of ghosts and presence of solution, in part at least Tarabinski solution, and some explanation of what does it mean such a model with essential singularity at infinity in the propagator from the quantum point of view. This model in principle has some relation to strings, because strings was one of the motivations for us to consider this model, and especially string field theory. In principle, this model has many nice properties, nice solutions, and a lot of things in principle were done. And I believe there are even more things yet to be done. We are still in the process of understanding inflation more in the framework, and I believe Sravan Kumar will speak more about relation of this model to inflation and to observables. And these computations related to quantum field theory toy models in this framework assure us that in principle there is a way to overcome the troubles which we see from the beginning, and it looks like that we just must work hard. Thank you very much.
Okay, thank you. Questions, please. We have time for a short question. No question. So I have a question. So is what you're doing, is this related in a some way of to the activity of Valery Frolov? Is it more or less similar or not?
It is, I believe, heavily related to activity of Valery Frolov, because he's at least his papers where he considered kind of this sort of Lagrangians exactly appeared after one day he discussed with me our paper a few years ago. Okay. So indeed it is related, yes.
Okay, so you say that you can get some physical solutions like bounces and all that.
Yes.
So explicitly.
Yes,
yeah?
Analytically, yes.
So in reasonable forms, which means
in a short form, yes. Exactly, scale factor equal cosine hyperbolic of sigma t, where t is time and sigma is a constant, will be exact solution to this action.
okay.
I mean, scale factor of a Friedman universe. Yes.
Okay.
Yes, in a very reasonable form, explicit metrics.
And so, okay, so this is the bounce, yeah.
Well, in particular, this would be bounce, yes.
Bounce, okay. Good, thank you. Maybe is there somebody else? Okay, thank you, Alexei. Then we shall move on to the next talk, which I believe is really on a related subject, or not? No.
Yes, it's related subject.
Sounds like related. At least
yeah, it's related. Okay, shall I start? Hello. Hello.
Yes. Okay. I can hear you. I suppose.
Okay. So shall I start?
Yes, of course. Yes.
Okay. Thank you very much for the opportunity to give this talk. Thanks especially to Mikhail Volkov and Dmitry Galtsov. And so I will be speaking about non-local R-square like inflation, which is very much related to the Lagrangians, what Alexei has presented in a previous talk. So I will first mention briefly about inflation and generic observables. Then I will mention R-square inflation, and then I will jump to the non-local R-square model. This is the work done in collaboration with Alexei Koshlev and Alexei Starobensky in these 3 papers, which appeared last year and before. And so let me just give introduction about what's all about early universe cosmology. It is everything what we want to explain this map, CMB map. Okay, so the physics we create to all is to explain the CMB map. How do we explain this? One of the very interesting paradigm to explain CMB is inflationary framework. Briefly, how does it work? So inflation is nothing but quasi de Sitter expansion. So this can be expressed in terms of the slow roll parameters, which are well known. So we have perfect de Sitter, and there is a departure from de Sitter. This is roughly the inflationary framework, and this solves several puzzles of the standard Big Bang cosmology. And to implement inflation, there are 2 ways. So we need to modify either left-hand side or right-hand side of the Einstein equations. And actually, in the literature, there are many models which modify the right-hand side of the Einstein equations. That means adding more hypothetical matter. And there are very few models which are based on the modification of left-hand side of the Einstein equations. One of the popular model is R-square inflation, which we will learn in the next slides. Okay, so let me give a brief summary of what are the inflationary observables. So there are mainly 3 observables related to 2-point correlations of scalar perturbations generated during inflation, and 2-point correlations of tensor perturbations generated during inflation. Okay, so and what the key parameters which we often hear is the spectral index, which is very much constrained by the latest Planck data, and there is also tensor to scalar ratio, which tells about ratio of tensor power spectrum to the scalar power spectrum. This is the parameter related to the primordial gravitational waves, and this has an upper bound. Okay, and there is another key parameter which is called the tensor tilt. It is not yet measured, but this is a very important parameter if we want to distinguish some frameworks of inflation and also some alternatives. Okay, and this is the current status of 3-point correlations. So if you look at CMB, if you look at 3 points in the CMB sky, so these correlations will tell us about the non-Gaussianities in the CMB, which means basically physically it means how the scalar fluctuations during inflation interact with each other. Okay, tree-level interactions. And with respect to all these parameters, scalar tilt, tensor to scalar ratio, and tensor tilt, there are two very important relations which tell us about characteristic of inflationary paradigm. If the inflation is driven by single scalar field, then these are the two consistency relations which must be obeyed. Okay, one is called the tensor consistency relation, which relates the tensor to scalar ratio and tensor tilt. Another one is called the Maldacena consistency relation, which relates the squeezed limit of 3-point correlation by spectrum with the NS spectral index. Okay, and what I will present in the rest of the talk is another counter example. Even though inflation is driven by a single field, we can violate these two consistency relations. Okay, this is the main essence of this observationally essence of this talk. So let me, as I said, so the model I'm speaking about is the non-local R-square inflation, which is the modification of Stravinsky inflation or R-square inflation, which was proposed in 1980 based on which is the model based on the modification of GR by R-square term. So we add a R-square term to the Lagrangian. So this gives inflationary evolution, which is given by this scale factor, okay, which is a solution of the trace equation of R plus R square theory. Remember, this equation is very much important, so we will come back to this equation. And okay, and Stravinsky inflation is the most successful model so far, with the perfectly matching with the observations, especially the spectral index and tensor to scalar ratio is within the limits of the current observations, and we have not detected yet. Okay, and there is a new parameter in the Lagrangian which is called the scalar en masse. So because this R square term will bring additional degree of freedom in the theory, and which is not a ghost for sure. So it is a scalar with a mass m much less than Planck mass. Okay, and this plays a key role in the observational predictions of this model, and this is constrained as this. And especially after the Planck data, Stravinsky model has gained a lot of attention because of its success with respect to these two key parameters. I will explain later. There is a fundamental reason why this model is really important, because it is motivated from our attempts towards quantum gravity. Okay, and let me also mention that Stravinsky model can also be realized by the right-hand side modification of Einstein equations by just doing a conformal transformation from Jordan frame to Einstein frame. And this basically motivated several frameworks within the supergravity and string theory. There are numerous models which kind of equivalent to Stravinsky model of inflation. So let me remind you that the motivations, the foundations of R-square model are Stravinsky inflation, which date back to the so-called conformal anomaly. Basically, if you start for GR with and put matter quantum fields and compute the expectation value of the energy momentum tensor, then we get correction to the trace of the energy momentum tensor, which contains several terms. One of the terms is box R. Okay, if you neglect the remaining terms, which are Weil and Gus-Bonnet, we end up with a trace equation of R plus R square theory. And this is called the conformal anomaly. And okay, we can speak a lot about this, but let me mention the main point of this. Okay, this is one of the first attempts of modifying gravity at very high energies, and this is well explained in this recent review. So this is the foundation because of the R-square model. So it is much more generic once if you want to quantize gravity. Okay, and as Alexei mentioned, if we add Weil square to the R plus R square, it is the so-called stellar gravity, which is renormalizable, but it contains a ghost. And how do we solve this ghost problem? This is again, this is basically the non-local extension of stellar gravity, which is Alexei already introduced us. Okay, and let me also mention why non-locality. So because now it is not only that if we want to extend the stellar gravity with finite derivatives, we end up with ghosts. Okay, if with infinite derivatives, we can remove ghost. But there are several other motivations. If we look at all the approaches towards quantum gravity, string theory that Alexei has mentioned in the previous talk. But even if you take any all the remaining approaches, causal sets or non-commutative theories or loop quantum gravity, and many of all the quantum approaches to quantum gravity has one common feature, that is non-locality. Okay, so in some form or another. Okay, so this is very important, crucial part. And the Lagrangians, which is extension of stellar gravity, non-local extension of stellar gravity, is described by this. And this Lagrangian captures all the feature of non-locality, and this is what we want to test with observations. Okay, and if we look at this Lagrangian, okay, this contains the infinite derivative operators like FR and FW, which are basically can be Taylor expanded, and they are analytic. And the challenging part is basically how to solve these equations of motion. So I will skip the historical details about why these theories are interesting with respect to quantum gravity. With a part of it is mentioned by Alexei. But let me get back to the solving these equations of motion of analytic infinite derivative gravity. Okay, so here we look at FRW case. That means, so if you see the Lagrangian, it has RF of box R and while F of box while, as it is known that while is 0 for FRW. Okay, then we can put all the while terms to 0 in the equations of motion. We end up with still complicated equations of motion. But as I said before, remember the trace equation of local theory, which is box R is equal to m square R, which basically means the Ricci scalar is eigenmode of D'Alembert operator. This produces a recursive relation, and through which, with some limited conditions on this form factor, this f of box, we can exactly realize we can exactly realize that this box R equal to m square R as an exact solution of this theory. Okay, what does it mean? We can have Stravinsky inflation as an exact solution of this theory. This is the most important point. But okay, it is a background solution, but perturbations will change because thanks to the fact that we have infinite derivatives in the Lagrangian. Now, let us speak about, okay, there is another, because of the non-locality, there is a new parameter we introduce, because when we put this f of box, we have to divide this box divided by some scale, and which we call it as non-locality scale. And intuitively, we can somehow put bounds on this non-locality scale. This is basically the physically we can put, and then later I will speak about observational aspects. So if we look at inflationary paradigm, as I mentioned in the beginning, it is quasi-de Sitter. That means basically we should have a nearly scale invariance, okay, in the Lagrangian. So if you look at the non-local Lagrangian, if you expand it in terms of all the box operators, so the first term R square term is scale invariant, and the remaining terms are not scale invariant. So with this, in order to have almost scale invariance, we put this non-locality scale above the Hubble scale and below the Planck scale. Okay, this is the range we can physically constrain. Okay, and there is a scalar on mass, so because we RF of box R will introduce a additional scalar in theory. Now let us study perturbations. How do we do? So we decompose the metric into 1 plus 3 in 1 plus 3 decomposition, we into the scalar and tensor part. And if we work out the equations of motion around this background solution, box R equal to m square R, we can realize that these two Bardeen potentials are related exactly like in local R square model. And perturbation of while is 0. So we left with only one part which contributes to the scalar perturbations. Okay, then we demand now, so far we did not put any constraint on f of box. Okay, so now we demand that the structure of f of box should be such that we do not have ghosts in the spectrum. Okay, we should have only one scalar, but not any more ghosts. So with this restriction, we can give a generic form of f of box, which leads to a theory with a propagating scalar, which is a scalaron with the same mass like in the local theory, and we do not introduce any additional ghosts. And this restriction will give us the same power spectrum as in the local theory. Okay, and there is another piece which I have already explained. We should have non-locality scale just above the Hubble scale during inflation. Okay, with this restriction, we preserve the good properties of local theory. That means the power spectrum and the spectral index remains the same, but the main difference with compared to local theory will come because of the while f of box while. So now we do the perturbations, and again we want the theory to be ghost free. Okay, then we demand that fw, there is a new non-local function in the Lagrangian between the while between the two while tensors, and we should demand this to be of specific form around de Sitter, and note that while f of box while will not introduce any sound speed for tensor fluctuations. Okay, so now given this form of f of box, we can have, in the theory we have only 2 degrees of freedom, 2 helicity, graviton helicity states and massless states. Okay, and there are no other tensor ghosts in the theory. Now given this, and given this form of f of box and this new factor while f of box while will change the tensor power spectrum compared to the local theory. Okay, this is the main difference, and this we can observe in the form of tensor to scalar ratio. So if we look at the local theory as Stravinsky inflation, which gives the tensor to scalar ratio roughly of the order of 10 power minus 3, and in this case, depending on the value of this new f of box, we can change this tensor to scalar ratio anyway above or below the Stravinsky model of inflation. Okay, prediction of Stravinsky model of inflation. And this is one thing. And as I said, there is another key parameter called NT, which is the tensor tilt, which is basically the derivative of the tensor power spectrum with respect to K. And this again gets modified because of this new term in the action while f of box while. And this is the signature of this non-local modification of R square inflation. And this something we can detect if we have in the future CMB and gravitational wave detectors. If the NT and R are detected, then, as I said, in the standard slow single field inflation, there is a consistency relation, which is R is minus 8 times NT. But in the case of non-local R square, we modify it thanks to this new term while f of box while. Okay. On the top of it, we also computed non-Gaussianities, that means 3-point scalar correlations. And so this is the key difference in the compared to local theory and non-local theory. In the local theory, okay, so when we take the tree level vertices, the vertex term is always some constant. Okay, so but in the non-local theory, all the vertex terms will carry some operator of box, which is exactly related to f of box as I presented in the Lagrangian. Okay, and this additional term, non-local term, will change the 3-point correlations, and this is what we have computed. And what the key result is, we have FNL deviated from the local theories. What is the most important point is the squeezed limit of FNL, which says about when we take the 3-point correlation, we should take the one of the momenta to 0. Okay, in this limit we have deviation from the local theory. This is the standard Maldacena consistency relation, which should hold in the local theory, but this is the correction due to the non-local interactions. And this is a new effect. Remember, we have only one scalaron in the theory, but still we have produced, thanks to the non-locality, additional corrections in this FNL squeeze limit. And this is a counterexample, and this basically evades all the known theorems about violation of Maldacena consistency relations necessarily requires multi-field. This is what we know so far, but what we have derived in the non-local context is it is not true. Okay, and this is the main observational signature about non-local R square like inflation. Here, what we have plotted is FNL and as a function of MS, the non-locality scale. Of course, we have chosen some particular form of f of box compatible with the ghost-free conditions, and we indeed have FNL of the order of 1, which can be achieved in this model, and this is a key prediction that we can say about this. Okay, so now let me summarize. Okay, so we have non-local modification of R square theory, which is very good improvement over stellar gravity. Now this action has very good properties related to quantum gravity, and one important feature of this model, there is non-locality, and this non-locality can be tested by two very key observables, which is modified tensor consistency relation and also non-Gaussianities. Okay, now there are open questions. What about if we add some matter fields in the Lagrangian coupled to the scalar in the theory? Okay, then how these observables will change? This is interesting for future investigations. And another theoretical challenge is there are these non-local form factors that are basically, you have this RF of box R and while F of box while, and this F of box, where does it come from? Okay, we do, for the moment we do not have principle to derive theoretically these form factors, but surely understanding perhaps more about string field theory or some other approaches called asymptotic safety, we may be able to constrain this F of box, and in which case we can put precise predictions about inflationary observables. Thank you very much.
Okay, thank you. Questions, please. Well, I don't know what to say because you apparently have solved everything already. Everything. So in this model,
we are still working on more improvements of this model, and there are some challenges. So yeah.
But tell me, so it's really a renormalizable model. So it's a renormalizable.
It is super renormalizable.
Renormalizable.
Yeah, if we take some specific form of this F of box, it is super renormalizable. Actually, that form is mentioned by Alexei in his last slide. So if you take some, you have this form factor, and you have this. It depends on some exponential of entire function. If you take some specific form of entire function, that leads to the some particular behavior of the propagator at infinity, then which makes this theory super renormalizable. But not always. Okay, it surely depending on the behavior of this entire function at infinity.
But again, do you need essentially to start from a conformally flat background, or you can start anywhere?
We can start, but then solving equations of motion is very tough. So because of this while term, we did solve actually in our last paper. We did solve for this model in removing this while term. We solved this Lagrangian for the Bianchi one matrix. But having this while term, it makes very difficult life very difficult to solve the equations of motion. Conformally flat is huge simplification because while is 0.
Okay. Then Jens has a question, so please.
Yeah, thank you. Thank you, Shravan, for giving your talk, and also thank you for staying up until 1:40 a.m. I know it's late for you guys in Japan, so much appreciated.
It's really a ghost time.
So I wanted to ask you this thing that I asked you a couple of weeks ago as well, which is the role of this scalar trace equation that you find from the local theory, right? This equation that box R is equal to m squared R, where m squared is the scalaron mass. Now you say you can use this to find a solution, and that I think that's very impressive. But my question is, also based on what Alexei was speaking about earlier, is there the possibility that there is a solution that you missed that way? What are your thoughts on this?
This question we tried to answer it in our paper, which appeared in 2017. Yeah, well, we proved a theorem about this, especially if you do not have any matter. Okay, so this just in vacuum, and the box R equal to m square R is the only solution for the flat FRW case. Okay, so and yeah. At least for FRW, we can basically say this. We cannot have any other solution. because it's a huge restriction in because of the you see the structure of Lagrangian is infinite derivatives, and the equations of motion is quite complex with infinite derivatives. So the only way to solve these equations of motion is to have some recursion relation.
Yeah, that's what I'm asking, because it's hard to have any sort of like general theorems on completeness of solutions of these equations, right? It's hard to say. So
yes, it is hard to say, but at least for this case, Ricci scalar, which is quite simple object. So even if you start with something like this, something like this, okay. So still you will end up with box R equal to m square or such kind of solutions. This is what we have proved it with some assumptions.
Thank you.
Alexei, yes.
Yeah, it's not actually a question, it's more a comment related to Jen's question. Indeed, we were proving in a paper with Ravan that as long as you constrain yourself to consider Friedman universes, you will not be able to construct anything beyond box R equal R1, box R equal m squared R. And in principle, even though there are too many derivatives here, it looks like system is very much constrained with some symmetry, most likely, which we don't understand yet. So let's say, on contrary to what you are suggesting, I would say that surprisingly, the system is hugely incompatible with any other solution. And in principle, in our paper from 2017, if I remember, you can find a very detailed proof of it. And we can discuss. It is indeed intriguing mathematical point, which we also were surprised when once we arrived to it.
Okay, fine. Then I think that we can thank Sravan for his talk, and then we pass to the next presentation of Tamas Malek, who will talk about, I suppose, the same theory. Well,
yeah, wait a second.
Please, okay.
Yeah, can you see my presentation?
Yes, yes,
yeah.
We can.
Okay, perfect. Okay, first of all, I would like to thank for the opportunity to speak on this conference, and I would like to present you solutions we found recently in solutions of infinite derivative gravity mentioned in the last two talks. And we found the exact solutions of infinite derivative gravity, which represents exact gravitational waves. So, and we use the special ansatz, so-called almost universal metrics. So let me start by saying a couple of words about. Oh, sorry, it's not. Ah, yeah. Okay. So and the almost universal metrics are. It's a very useful ansatz, which can be used for solving any higher order gravity theories, where in the Lagrangian there is any curvature invariant constructed from the Riemann tensor and its covariant derivatives of any order. So, and the field equations of such theories are of this form. The matter part gives the energy momentum tensor, and on the left hand side the tensor EAB is obviously symmetric conserved rank 2 tensor, which is constructed only from the Riemann tensor and its covariant derivatives. And if you want to solve such field equations, so they are very complicated, so you have to use some convenient ansatz. And the simplest ansatz ever you can use for solving such field equation is is a maximal symmetric spacetime. If you plug maximally symmetric spacetime to the field equations, so the field equations of any higher order gravity theory are reduced to just actually algebraic equation. This lambda equals 0. This algebraic equation which determines the value of the constant which is scalar. So maximally symmetric spacetimes are Einstein spacetime, so the trace-free Ricci tensor vanishes, and conformal flat, so wild tensor vanishes, and Ricci scalar is constant. So therefore, all the information about the curvature is described by the constant Ricci scalar, and these spacetimes are very trivial. So we can generalize this very simple ansatz a little bit if we relax the condition on the wild tensor, and in this way we can obtain so-called universal metrics, which for which the field equations of any higher order gravity theories reduce again to the just one algebraic equation. So the rank 2 tensor EAB is proportional to the metric, and the lambda equals 0 gives the algebraic equation which determines the. Sorry.
What is F S TF Ricci S is equal to 0? What is S?
S is trace-free Ricci tensor.
Okay.
S is trace-free Ricci tensor, and C is wild tensor. R is a Ricci scalar. So this is my notation.
Okay.
Okay. So these are the universal. So and even and there are many examples of universal metrics which are of algebraic type 3, n, even some examples of type 2. But still, they can be used for finding vacuum solutions of higher order gravities, because this tensor EAB is proportional to the metric. So there is no non-trivial energy momentum tensor which is compatible with this. Just so, so we can, if we want to find non-vacuum solutions, we can generalize the universal metrics a little bit again by relaxing the condition on the trace-free Ricci tensor. So now the trace-free Ricci tensor has one component. It's proportional to L. L is null vector. So wild tensor is non-vanishing, and for almost universal, so we call them Tn because the trace-free Ricci tensor is of type n. It has only this component. So for those almost universal Tn spacetimes, the field equation reduces to this form. So there is again term proportional to metric, and the one. So this is the trace of the tensor EAB, and this is the traceless part. And there is a special subclass which we'll use for the derivation of our solutions of almost universal spacetime, which is called TNS. The S here means that for this special subclass of almost universal spacetimes, this term here can be written in this form. So it's just box on trace-free Ricci tensor. Yeah. So this allows us to, and as you can see, so the almost universal spacetime, these rank 2 tensors are compatible with the energy momentum tensor corresponding to null radiation. So which will we employ later. Okay, so this is our ansatz, and we will consider this Lagrangian. So it was mentioned already several times, and it is the most general action quadratic in curvature, which is parity invariant, and we will consider these form factors to be analytic operators, which then lead to Gauss. Because we will get rid of Gauss by this choice, and we introduce this L, which describes the length scale of non-locality, which is hidden here in the form factors. So yeah, as I said, it's more general, and in this form, the L, if L goes to 0, we recover the GR with cosmological term. Okay, and yeah, as I already said. And the field equations are very complicated of infinite derivative gravity. They are nonlinear, and because they are quadratic in the curvature and non-local. And but we can use the special property of the TNS spacetimes, of almost universal TNs and spacetimes. The most important property is that the trace-free Ricci tensor and wild tensor and its covariant derivatives, they contribute to rank 2 tensors only linearly. So all these terms here vanishes because they are quadratic, all the omegas, and Ricci scalar is constant. So all these tensor and scalars vanishes, and actually there survives just terms like, for example, this nabla nabla f3 while, but we can use some useful identities for TNS spacetimes. So everything which still survive in the field equations can be rewrite in terms of box of D'Alembert operator and the trace-free Ricci tensor. So the field equation reduced to this form for TNS spacetime. So there is a trace part, and this is the traceless part. Yeah. So the field equations are now linearized in the sense that the curvature is just linear, appear linearly there, but they are still non-local. So this is nice property. We have still here the form factors, and we can reduce the field equations furthermore because for almost universal spacetimes, the trace-free Ricci tensor is of type N. So it has only this one component. This is standard notation from Newman-Penrose formalism. And the D'Alembert operator on S can be rewritten in this form. So for almost universal spacetime, so the null vectors L factors out, and we introduced the operator D here. So we assume that the energy momentum tensor corresponds to null radiation. So it has only this component, and therefore the field equations reduces to just one algebraic equation which determines the value of the constant Ricci scalar, and one partial differential equation for the component of the non-vanishing component of the trace-free Ricci tensor, and J is the source. Okay, so and yeah. So, but so far we haven't employed the explicit form for the metric, and so it can be shown that TNN spacetimes are necessarily algebraic special Kuhn spacetimes with constant scalar invariance. And on the other hand, all Kuhn metric of wild type N and trace-free Ricci type N are TNS spacetimes. So we can choose any such metric, and it's ensured that it's TNS spacetimes. So so Kuhn spacetimes are defined geometrically as metrics which admits congruence of null geodesics with non-expanding shear, twist, and shear, and the metric in general can be written in this form, where the function h is real, w is a complex function, and p is a real function, and this transversal 2 space characterize the geometries of the wave surface, where the wave gravitational waves are propagated along the null vector L. Along the Kuhn, which is the Kuhn non-expanding, non-shearing, non-twisting null vector. Okay, and for wild type N and trace-free Ricci type N, the metric function takes this form. So there is only this function h0 is the only. This is arbitrary function. And A and B here are arbitrary functions of U, and H0 is arbitrary function of U and zeta bar. And yeah, and for those metrics, the component, the only component of the trace-free Ricci tensor is given by the delta operator and the function h0. So, and the nice property is that this delta can be rewrite in this form where this triangle is just it's a Laplace operator on the transversal 2 space, or which is maximal symmetric for wild type and trace-free Ricci type and Coulomb metrics. This is very nice property. So the field equation finally reduced to this simple form involving just the Laplacian on 2 spaces. And yeah, and now we have to choose the form factor. So we will require that the independent number of the solutions of the homogeneous part of the solution is the same like in the local case when where the L, the parameter of non-locality, goes to 0. So, and therefore we require that G is the operator G is has no 0, so it's exponential of entire function. And moreover, we then choose this entire function just to be L squared times Laplacian, which allows us to use the heat kernel method to solve the field equation. And okay, and this choice is actually compatible with ghost-free condition in anti-de Sitter and de Sitter background, so it's correct to use it. And now, so this is the field equation for the unknown function h0, and J is the source, which we have to prescribe the source and solve for h0. So, but this is just the equation involving the Laplace operator on 2 spaces. So we can use the eigenfunction expansion, which is known. So we can solve the solution, look for the solution. We can just formally rewrite the solution in this way, and we have to just prescribe the source. So which source to use? We can look at the known solutions of GR for inspiration. So in the case of vanishing cosmological constant, we can yeah, it's a known solution, Eichelburg-Sechsel, which was obtained by boosting Schwarzschild metric to the speed of light. And this solution corresponds to impulsive gravitational waves, which are generated by null particle located at the origin in polar coordinates on the transversal space, which is Euclidean. And for the Eichelburg-Sechsel solution, the source looks like this. And so this we can take this source, we can get this J as our source, and we replace the delta function by arbitrary wave profile function, and we plug this source to our field equation. For in the local case, we obtain the generalized Eichelburg-Sechsel solution. Okay, this is a bit in local case, but in the full non-local case, we were able to derive the exact solution as well. So this is the exact solution in the case of vanishing cosmological constant. So, and in this plot here, you can compare the blue dashed line is corresponds to the local solution, and from the previous slide, and the red line corresponds to non-local solution. So as you can see, the local solution diverges at the location of the source, whereas the non-local solutions is finite at the location of the source. It's a nice property. And if the parameter of non-locality goes to 0, or if we are far from the source, which means that L is much less than high, we recover the Eichelburg-Sechsel solutions of GR. So yeah, so the limit exists. So okay, this is the case of with vanishing cosmological constant. Similarly, for a positive cosmological constant, we can take the Hotta-Tanaka solution, which is again the solution, GR solution, which was obtained by boosting the Schwarzschild de Sitter metric. And in this case, it represents impulsive gravitational waves generated by two null particles, which are located on the opposite poles of the two sphere in the transversal space. So there are two sources. And again, using this source, we can find the local solution and a non-local solution. So again, and yeah, and in the limit where this sigma goes to, which is just rescale the parameter of the non-locality. If this sigma goes to 0, we recovers the local GR solutions of the Tanaka solution. So again, here the blue dashed line corresponds to local solution, which diverges at the locations of sources at the high 0 and high equals to pi, and there are several examples of non-local solutions, and they are finite and the locations of the sources. And similarly, we can find solution for in the case of negative cosmological constant, and there is again just one source, one null particle located at the origin of the hyper space. Okay, so all these solutions are regular. Non-local solutions are regular at the locations of the sources. But the question is whether they are also free of the curvature singularities. And the almost universal spacetimes, as I already mentioned, they are CSI, which means the constant the scalar invariants are constant, and therefore they are free of scalar curvature singularities. But they can still possess a so-called non-local, non-scalar curvature singularities, which happen in the GR case. And to answer the question whether these singularities are located at the positions of the sources in the non-local case, we have to study all geodesics, null and timeline geodesics passing through the locations of the sources, and then check the components of the curvature tensors in parallel propagated frames in all these along all these geodesics. So it's very complicated, even in the case of vanishing cosmological constant. So we left it for future works maybe. But as a hint that the curvature, these solutions are free of the curvature singularities at the locations of the sources, can be we can calculate the components of the curvature tensor in the nature frame, and for all these local solutions, the wild tensor, the components of the wild tensor psi4 diverges at the locations of the sources, and on the other hand, the components of the trace Ricci tensor and components of the wild tensors are finite, or in the case of for the non-local solution. So this is it's just a hint that these non-local solutions are free of curvature singularities, but it's not proof. Okay, and yeah, if you are interested in the almost universal spacetimes or these non-local gravitation waves in non-local gravity, these are the references, and that's it. And I thank you for your attention.
Okay, thank you. Very interesting. So, but look, you have formulas for arbitrary source, and then you consider just the source of Hilbert-Sexel and Tanaka and right. But in principle, you can apply it to any source.
Yes,
right?
yes, right. But we wanted to find some known solution, GR solution, existing GR solution, and look what happened if we take the same source in non-local gravity.
Oh.
But you can, in principle, you can plug any to the equation. You can put any arbitrary, yeah. So the J can be arbitrary completely. So.
For example, if you just choose a time-dependent quadrupole, like, you know, to reproduce, can you reproduce the usual quadrupole formula in GR or analog of this quadrupole formula?
Mm.
So
is it null source? Because we
well, no, it's not noise. So you need null source.
yeah, but
Right,
J is arbitrary, but it's a null source because
okay, I see.
the energy momentum tensor is of this form. So J is the only component of the energy momentum tensor, where L is null vector. So it's arbitrary null source. Yeah.
Can you choose light rays or something like that?
Light
rays.
Yeah.
So light gravitational wave produced by light. So
yeah, actually actually the Hotta-Tanaka and Hilbert-Sexel solutions are solutions where the gravitational waves are generated by null particles, which could be light or any null particle. Yeah.
Okay.
So.
Interesting. So apparently this one can do something in this theory. Yeah.
Yeah.
Okay. So please, somebody else maybe has other questions. Okay. But this is all published.
Yeah.
As you said.
Yeah.
Okay.
You can. It was. I think it was published last week or something. In this paper in PhysRevD. But you can find it on arXiv as well.
Okay, thank you. If there are no questions, but thank you very much. I personally find it very interesting.
Yeah, thank you.
Then let's move on to the last presentations of Jens Bose. Okay, so
right.
please. Okay.
Can you see my screen?
Yes, I can. At least I suppose everybody can.
Yes.
I think that's true. Yeah. Okay, great. Anytime you're ready. Okay, so it's great to be here again at Marcel Grossmann number 16. I remember Marcel Grossmann number 14, which was in Rome, and it was 37 degrees and it was very, very hot. And so this is an advantage of maybe the fact that we can do this during a pandemic, so we can do this at home with air conditioning. But it's kidding aside, it's nice to be here and to be able to give this talk to you. And you'll see that this is about ultra-relativistic spinning objects in, again, non-local ghost-free gravity. So I'll be touching on a lot of different aspects from previous talks. And this is also an answer maybe to Alexei's question earlier. So about and also your question, Mikhail, earlier, whether Valery Frolov was working on this or not. And you see here, he was my PhD advisor in Edmonton, and we worked on this quite extensively on these non-local theories in about 10 to 12 different publications.
Okay, I see it indeed. Yeah, right. Okay.
All right, so this is based, today this work is based on a paper with Jose Pinedo Soto, who was a master's student in Edmonton, and Valery Frolov, who was then my PhD advisor. And this is also published here in Physical Review D. And much of this is also based on work with Andrei Zelnikov, who is also in Edmonton. So I'm going to keep this part here short, but just briefly, why would you want to think about non-locality to begin with? Well, there is a long-standing problem, as we all know, which is singularities in physical quantities. And so this could be some observables, some amplitudes in quantum field theory that diverge. It could be the curvature in general relativity, but it could also be something else that blows up for some reason due to our ignorance of the UV physics. So what we can do if you want to fix this is, of course, we can use regulators, and it's useful to use regulators that are consistent with the symmetries of the theory, and it's called covariant regularization. And one example, famous example, is Pauli Villar regularization, which you see sketched here. So suppose this is in the context of quantum field theory, of course, but suppose you use a 1 over p squared massless propagator, something like that. You could add a mass there, doesn't matter. And you modify this to include additional mass terms, higher masses, M1, M2, they're much larger than the typical scale. Then you see that this improves the ultraviolet behavior, because then these ones here become negligible if you move this to Euclidean space, and then you have higher suppressed propagators, and that usually leads to improvements in the theory. And of course, in the limit that these masses go to infinity, this decouples and you're left back with your original theory. Now, the problem with this, of course, is that if you do a partial fraction decomposition of this sort of expression here, and this is just for 2 masses, you can do this for any number of masses, you find that there is this generic structure here, so you get additional poles at these masses M1, M2. I mean, that's expected. But the problem is, if you take this equation here and multiply this with p squared, with the Euclidean p squared, and send p squared to infinity, then you see that 1 plus C1 plus C2 plus all these other coefficients, if you have them, have to add up to 0. And that means that some of these coefficients have to be negative, because the first one is always positive. And of course, that means that you will in general have negative norm states. And you can try to make sense of it. You can say, let's do what Lee and Wick did and try to understand this as a feature, because I mean, these opposing signs here, they lead to cancellations of quadratic divergences. So it's something that's desirable, but you can't have them on external legs. You have to constrain them to internal lines only, because otherwise you have macroscopic causality violation. And so there's some sort of issues. Also, if you use these things in gauge theories, then you have issues with pinching of control lines. So you have to use some type of Klopp prescription to maintain analyticity properties. So this can be a little bit annoying. So what else you can do is just you can get rid of these degrees of freedom with non-locality. And this is what the previous presentations already touched on quite a lot. So instead of multiplying 1 over p squared with these factors, you multiply this with an entire function. In this case, I just used e to the p squared by m squared. And that one does, I mean, obviously, if you insert a Euclidean momentum, it's going to lead to regularization. It's going to make the propagator, pardon me, exponentially suppressed. But you don't have any other poles. And one way to think about this is you can write this as a series expansion, but just as a product expansion of the exponential here, where the masses mj are chosen suitably to generate this sort of form. It's always possible. And one of the earliest references for this kind of approach was Krasnikov in '87. But I also want to toot my own horn just a little bit. So in a recent paper with Chris Carone, who is here at William and Mary, we used this kind of model here to interpolate between a Lee-Wick theory and a non-local theory. And that can be quite useful for certain applications. For example, the hierarchy problem, study the divergence properties of scalar self-energies or something in quantum field theory. Okay, so since non-locality plays this important role also in other fields of physics, for example, in quantum information, quantum entanglement, also in observables and quantum gravity. In this work, we just consider non-locality as a feature, not as a bug, and we just aim to generate some sort of non-local intuition, whatever that means. So again, here's the action that we use as our starting point for non-local gravity, because I could talk more about quantum field theory, but this is a gravity conference, so I want to talk about an application to gravity here. And I'll be talking about the linearized theory today, where we can use green functions. So as we have seen, nonlinear equations are quite complicated, but in the end, there might be some sort of relation. I'll get back to that towards the end of my slides. Okay, so let's take this as the starting point here. This is an action. That's just the Einstein-Hilbert term. We're not bothering with a cosmological constant here. And then you can add quadratic terms and with this operator O mu in the middle. And you can use this to reproduce a stellar gravity, some sort of models like this. You could even have parity odd things if you wanted to. But in this case, since we're interested in non-local gravity, we are allowing this to depend on covariant derivatives as well. And then you can convince yourselves what kind of terms you can add, how many derivatives you're allowing. I mean, there's obviously a limit in terms of covariant derivatives because you can only saturate 8 indices, but these boxes, they can show up at arbitrary powers. And that's essentially, in the end, what gives rise to non-locality. Now, at the linear level, this is all a lot easier because that's what you are left with. You can show from symmetry considerations, gauge invariance in particular, that you can only have 2 independent functions of the box operator that is at the linear level when you are expanding around Minkowski spacetime. So h mu nu is my perturbation around space about flat Minkowski spacetime. So you have these two functions a and c, and this is how it looks like. And you also see, maybe you recognize this, if you set a to 1 and c to 1, then you just get the Fields-Pauli action, which is maybe what you would expect. So this all makes sense. And the only thing is, what if a and c are not the same? And you can show when you study, for example, the spin projection operators for this action, or for this generalized Lichnerowitz operator, you can just show that a has to be equal to c, because otherwise you have additional degrees of freedom. So that's the equivalent of what we saw earlier as the ghost-free condition. So there's no additional degrees of freedom running around. And when you derive the equations of motion, you find a very simple structure here, which is just a of box h mu nu is equal to t mu nu. And of course, this h mu nu here, as usual, is the trace reversed metric perturbation. But this is a linear equation in h mu nu because this is a weak field expansion. And also A is a function, like I think Alexei mentioned this very nicely earlier, that we assume this to be invertible. So you can define an object that I call the effective energy momentum, which is basically the original one, and you just multiply this with the inverse of this operator. This is just a formal sort of like relation. You can think about it this way. And if you want to have some sort of idea of what kind of A of box of form factors here we deal with, this is the famous E to the box theory. It could be other theories, but this is the one that we ended up working with in the end of the day. Again, this lowercase l here is the scale of non-locality. So you see, if we put that one back to 0, then these scale factors all become unity, and we end up with linearized Einstein gravity. And our idea is, well, now that we have this equation here, we can try to solve this with a green function method for a given source. And mentioning static green functions, we're going to focus on static examples in this talk because it's a little bit easier. And then we don't have the box operators, but we just have the Nabla square or the Laplace operator. And we define our spatial green function calligraphic G sub D. So it's the spatial green function in D dimensions with this usual definition here. So notice that the differential operator is Nabla squared A of Nabla squared. But of course, again, like before, you can invert this and put this to the other side. So you can also think of non-local green functions as solutions, not for a delta function, but for an effective delta function. Here's one way to think about this. And when you compute this for a specific form factor, the delta function typically becomes like a Gaussian, that whose width is proportional to the scale of non-locality. When you set that scale of non-locality back to 0, then you end up with the original delta function, and you're back in the local theory. This is a technical result that we found together with Valerie Frolov and Jose Pinedo Soto, and it's quite useful because it allows you to express this spatial green function in terms of a d-dimensional heat kernel in imaginary time, which is this object calligraphic K sub D here. And the nice part about this is you can ask yourself, okay, these are two integrals, and we proved this in this paper here, but how the spatial information enters the green function. This is very simple in this picture because it just enters through the exponential here. That's the only place where it adds. And that's also very nice when you work in, for example, in Cartesian coordinates, because it's just going to be a product of x squared, y squared, z squared, because it's in the exponential. So it's going to all decouple really nicely. And we'll use this later in our computations. And of course, this doesn't just work for just non-local theories. It works for any theory that can be written in terms of a form factor, where you can define in this integral here, this inverse, and it doesn't blow up during the integration domain over the real line. If you have an operator like this, then you can do it. So today I want to talk about something simple, just a spinning pencil that is infinitely thin. So we imagine this to be extended along the C bar axis here. And then there's just a bunch of transverse directions that I call x subscript perpendicular. And it has a length of L bar in its own rest frame. And it also has a mass line density. So we allow for non-homogeneous line densities along this, and also for a non-homogeneous angular momentum density. And all these objects are decorated with bars because they're in the rest frame of this pencil. So we put that aside. And well, in these coordinates, then the energy momentum tensor takes this specific form here, which is, expected, right? This is just the energy density. And then there is here this funny looking term, which is just the angular momentum density. And because it's a cylinder of, well, I drew it with some finite thickness, but really should think of it as being infinitely small, of course, there's a delta function right here, the d-1 dimensional transverse delta function. But because the energy momentum tensor is so simple, because it has a delta function on the right-hand side, the solution is going to be just a very simple integral over the green function. So here I just write down what is the solution. This isn't, I mean, of course, an exact solution because it's a linear theory. So it's not that hard to find it, but still, this is the form that it takes. So you see there's this potential phi bar, which is just sort of like the analog of the Newtonian potential. And then there is this A sub I, which is the gravido-electromagnetic potential, which is caused by the rotation of the cylinder. And then you can look at these expressions, and of course they involve integrations over the xi bar direction because we allowed for these non-homogeneous mass distributions. Okay. You notice also here that the d-dimensional green function enters, and also the d+2 dimensional green function enters, and that is because you can see the rotation here comes with a derivative, and you can show using this previous representation of the green function that if you act with a derivative on it, that you get a higher dimensional green function. So these are methods that you can use to simplify your expressions. So now the idea is to take this cylinder, which is just some solution that you can find, and boost it. In particular, we boost it along its symmetry axis, so along the xi bar direction, all the way up to the speed of light in a suitable limit. Because of course you can't boost a massive object with the speed of light. It's not well defined because the Lorentz group is famously compact. So you run into all kinds of problems. But what we can do is we can define this thing that Penrose in '76 introduced, and in his honor, we call it the Penrose limit. And what that involves is that you assume that during the boosting process, certain parameters of your solution multiplied with the power of the Lorentz boost factor remain constant. And so in our case, it means that the pencil length, we demand that gamma divided by L bar remains constant, which means that as we boost it closer to the speed of light, we kind of like stretch the pencil and make it longer to counteract the Lorentz contraction. The pencil mass is going to be taken to 0 as gamma approaches infinity, so that this product here stays finite. You can think of it as an asymptotically null solution that we end up with this way. And also the total angular momentum is just kept constant. And one way to think about why this makes sense is because angular momentum, in this case, we assume that it only rotates around its symmetry axis. And this means that this angular momentum is all aligned with the boost direction, which means that the tensorial components are all in the perpendicular space. So they're left invariant under a boost. So it's convenient to, of course, work in retarded time, which in the ultra-relativistic limit just takes this relation here. You can relate xi bar in the old frame to the new variables, which are the unbarred variables t and xi, or also here just u, which has this relation here. And there's a gamma factor that is sitting in there. So we have to kind of deal with these kind of expressions, but using these Penrose limiting identities here, we can absorb all diverging factors, except for one. And that's important, because there's going to be one factor that stands in front of the Green's function. Because remember, in our final expression, the way that our geometry looked like, we wrote it in terms of all these d-dimensional or d+2 dimensional Green functions. And using our heat kernel representation, it's actually possible to take this Green function and compute this limit here. So gamma, which goes to infinity, times this d-dimensional Green function dependent on r bar. And r bar is just this spatial distance, right, that we needed for, during these Green function integrals. I mean, here you see how this looks like. This is just a orthogonal sum of the perpendicular space and the distance in these retarded times. And of course, those, because of this gamma here, they also pick up a gamma squared here. But the remarkable property is, at least we found that you can write this limit, which looks very, very singular, using this heat kernel representation. You can write it as a very simple thing. It's just a d-1 dimensional Green function of the transverse space multiplied by a delta function in the retarded time. And of course, that makes everything simple, and it makes these integrals that we initially had, it just makes them collapse. So the resulting metric that we get out of this Penrose limit is what we call a non-singular shock wave. And I'm aware that this sounds a little bit crazy because a shock wave is singular. Why do we call it non-singular? So I'll comment on this right now. So this is how the metric looks like. You see that d by dv, so the advanced time direction, is a null killing vector of this metric, which makes this a pp wave. And these potentials phi and a that are featured in this new metric, notice I don't have bars anymore because they're in this new moving frame. They take this particular form here. Now, don't mind these funny looking prefactors, but see that are given just by these green function d-1 and d+1 dimensions. Yeah, so multiplied by these functions lambda of u and jij of u, which are just, you know, how the mass density and how the angular momentum density looks like in that ultra relativistic null frame in the end of the day. The first thing to notice is that this metric is regular at r perp equal to 0. So if you are at the location of the source, the spatial location of the source, these functions here, these calligraphic g sub d's, these are the non-local green functions in these spatial dimensions. They're all finite as r goes to 0. And that's, of course, very different from the local theory where you have them blow up like 1 over r squared, or log of r, something like that, right? So this is really an effect of any non-local or any regular theory, really, that this is a metric that is regular at the location of the source as it impinges these null hypersurfaces. So in that sense, it is non-singular. Now we took initially not a point-like particle, but a pencil, meaning it has a finite duration or a finite distance in the boost direction. But if you were to take initially point-like particle, then the resulting metric, instead of these lambda of u or jij of u, it would contain factors of delta of u, right? Just from this property of the green function. And of course, in that sense, they would still be singular shock waves just because they're localized precisely at u equal to 0. But that's just like a light ray, right? A light ray has the same kind of behavior. And when you take this metric here and you consider a point-like particle, then lambda and jij, they just become, they drop out and they become essentially delta functions. This becomes this Eichelborg-Zexel-Giraton metric that Tomáš has already mentioned in the previous talk. So I'm quite glad that he gave his talk first, because I'm just throwing this out here, but he mentioned this, and this is exactly what you get.
Wait, I'm a bit lost because after all, you're considering the linear theory, right?
Yes, exactly. That's exactly the interesting part. So exactly. So this is not a solution in the strict sense, because we take a linear theory, compute some solution, we boost it, and then we get some geometry out of it. But it turns out that in the local case, so I'm not speaking about non-locality right now, but in the local case, this is exactly the same as the Eichelborg-Zexel solution that you find in nonlinear GR. There's a one-to-one correspondence between these things. And the reason is just that, well, it's what Tomáš was talking about, right? That non-linear equations, if you have a null structure present, they can drastically simplify, essentially because when you square something null, it becomes 0. So, I mean, I'm grossly oversimplifying this. You saw how difficult it is to do these computations, but you can prove it that this metric here in the local theory is just the Eichelborg-Zexel metric. Yeah. So it's a surprising result.
Okay.
And you can take this and apply this to more general settings. So you may say, okay, why did you take a cylinder? So in my PhD thesis, which you can find on the archive from September last year, I applied this to p-branes. I mean, arbitrary spatial dimensions and codimension, and you can give them angular momentum densities, mass densities, and then you can boost them as well. And there's similar expressions just like those ones. And so this is not a thing that is particular to like the cylinder or anything like this. So this kind of prescription works for all of these things. So I set my timer to 20 minutes. So I think we have 5 minutes left. So I'll just summarize really quickly, and then maybe you have some time for questions. So these studies, I think, are interesting to some extent because they show you that non-local ghost-free gravity typically gives you finite gravitational fields at the linear level. And these are exact solutions, but that's just because you can use, well, the green function method approach. And this ultra-relativistic objects, these are interesting, I think, because they allow you to study a little bit of the space-time properties of non-locality, because you start with something that is time independent, you boost it, and you have something that depends on your retarded time. So there's some sort of time dependent that emerges through this Penrose limit, which is quite interesting. So the Penrose limit is certainly quite a powerful method to generate geometries. But is this solution an exact solution? I'm glad that we have Tomáš with us today, because I will ask him afterwards. If nobody asks any question, I will ask a question. Because of course, as you saw, the nonlinear problem in general is infinitely complicated, because you can't just truncate your exponential or your form factors. You have to take all the orders, and it's going to be very, very, very complicated. So it's an open question if these Duraton metrics that we find, specifically the one that I showed you today for the pencil, if that is also a solution in the non-local theory. It's probably, well, it's probable that it is, but we weren't able to prove it. But it might be possible in the future to show that it is an exact solution, or maybe it isn't. And the last thing I wanted to mention is just that it would be very nice if, you know, these form factors, if we found some sort of principle that would, you know, let us single out a form factor, because we just use this e to the box kind of theory, and it works. And yes, it's predicted from string field theory in some context. But why that theory, right? Why not something else? So it would be nice to find out what kind of form factor is predicted from a more fundamental concept. But that goes beyond this talk. And with that, I want to thank you very much for your attention. Thank you.
Okay, thank you. So you did not know in advance that your solution was exact, right?
This is, I mean, this is not a solution, right? This is what we find. This is just a resulting metric, because we took an exact solution, we just boosted, and then we just obtained something, right? So this isn't even a solution. I'm not claiming that this is a solution of the weak field theory. I mean, you can do this, you can show this, you can, you know, boost the energy momentum using similar scaling relations. Yeah, so this is doable. But the fact that this Eichelborg-Zexel metric, that it corresponds to this 1-to-1, this is very surprising. Yeah, but I mean, we were not the ones who found this, right? I mean, this has been known for a while. We just try to see what happens in the non-local theory.
Okay.
Yeah, but it's not clear, and it's also interesting that in 4 dimensions this works, but in 5 dimensions it doesn't. So people have solved the Einstein equations for ultra-relativistic objects in 5 dimensions. But as you saw, right, in these considerations here, we kept the dimensionality open, right? So I could easily write this down in 5 dimensions or 27 dimensions, whatever. If you do this in 5 dimensions and you write down what the local solution would look like, you would basically get the 5-dimensional Eichelborg-Zexel metric. This one is not an exact solution of the 5-dimensional Einstein equations. So there's something about 4 dimensions in here as well. That's interesting.
Mm-hmm. Because in higher dimensions, different green functions, maybe this.
Of course, yes, the green functions are different. There is something interesting that happens in 4 dimensions, which is that if you look at this gravitomagnetic term here, so if you work it out, what it becomes in terms of a 1 form. So if you consider AI dx perpendicular I, this just becomes an exact form. This just becomes a constant times d phi, phi being the, you know, the rotational angle. This is in 4 dimensions. So in particular, dA is equal to 0 almost everywhere. So this is a very special thing that happens, but only happens in 4 space-time dimensions. And of course, that looks very different in 5 dimensions. So that might be one of the reasons. Yeah.
Okay, good. Thank you. Maybe there are some other questions. So please, the others. There are specialists in the audience. I am not a specialist in this business.
Okay, maybe I have just a comment.
Yes.
That we are just finishing a paper on exact gyrotons in infinite derivative gravity, and the field equations are not linearized for gyrotons, but they can be solved because there are two unknown functions which has to be determined, and so if you obtain like two equations, one equation is linear, the second is not, but if you find the solutions of the first equation, you can plug this solution to the second, and it becomes linear as well. So yeah, and we are just finishing paper, so I think it will appear, I don't know, within 2 weeks, maybe 3.
Okay, this is with
on
Ivan,
archive.
right?
Yeah, with Ivan. Yes.
Yeah. Tell him I said hi. This is interesting. Can you spoil anything? Is it does it? I mean, you probably saw the paper that we did on this because this is the first paper on these Durotons and non-local theories. Does it look similar to leading order, or do you get something entirely different?
Yeah. To leading order is the same, I think. Yeah.
But there are differences. Really,
but they are not they are not. The linear solution is not exact solution. Yeah.
That is interesting.
But,
that is interesting. Thank you so much.
Yeah.
Yeah, I look forward to that paper. 2 weeks, you say? Okay, that's good. That's
I hope
during the
maybe
summer
3.
break, so I can read it. Thank you.
Yeah.
Okay, good. So if there are no more questions, then let me thank everybody for your presentations. And so our section is over for today, but there will be a continuation on Thursday at the same time. So if you're welcome back to listen to more of this stuff. Okay, thank you everybody. Then have a good time.
Thank you everybody.
Yeah, bye.